And this has to play again is important because this is not working.
Try the other one. You have two there, right?
Can I do something here on the board? I need to wait. So I will continue, and they are solving the problem. No, okay, it's already done. Okay, thank you. So it is not mandatory to close a block, but whenever a player closes a block, it's mandatory to play again. So the players will continue to do it, and whenever all edges are drawn, the game is over, and who has more boxes wins the game. So probably many of you play this during math classes, I don't know, but it's a very famous game. So here the final result was 16 for Alice, 9 for Bob. Alice won the game. And since Edward Lucker's proposal, there are a lot of commercial proposals, but in my opinion, there is nothing better than playing with pencil and paper. And I cannot talk about these games without mentioning a very important name, that is Elwin Berlekamp, here on the right, on this picture. He dedicates most of his entire life to this game. A key reference is this book, the Dots and Box game, Sophisticated Child's Play. And to understand the things that I'm going to mention during the talk, we need to know the power of a move called double dealing move. And that's what I'm trying to explain. What is a double dealing move? I don't know if you know the term, but that's my goal here, my first goal. So imagine we have this position, and imagine that Alice will start playing this position, and she's very greedy. And by greedy, I mean that she will close all the boxes she can. So by being greedy, she will take all the boxes, and look, since she played here, she has to play again, and now she played here, and now it is Bob's turn, and imagine that Bob is also very greedy, and he will close all the boxes, and what happens here is that they will close all the boxes. I will go forward quickly, and the game is a draw if both players are greedy. The final result is a tie. But now let's go back to the beginning and let's be smart and let's think a little bit and improve our strategy. And imagine that now Alice will pick some boxes, but there is a key moment here. Is this moment. In this moment, Alice has the opportunity to close the last two boxes and play in the new chain, or she has the opportunity to sacrifice these two boxes, but control the game by giving the turn to Bob, like this. This is what we call a double dealing move. And by doing this, now Bob will take the two boxes, but now it's Bob that is going to open the chain. And now Alice will repeat the strategy. She will get all but two boxes, and again, a double dealing move, and Bob has to take the two boxes, and the thing is repeated. The move that Bob does here, this is a double dealing move, and this move made by Bob, it's a double crossed move. This is also important for the later on the conversation. So, in the last long chain, Alice can take all the boxes because she doesn't need any more to maintain the control, so she gets all the boxes, and the result is very different from the one if they are greedy. And a final remark about this position is the following. We have in this position 4 long chains, and we had 3 double-crossed moves. So in general, the number of double-cross moves in the game, when the players are good, are one less than the number of long chains. And this is very important to improve our gameplay. So here it was already mentioned our championship. Here is, I will use one example, a real example from the championship here in 2006. We are already in the 18th edition. These kids must be in their 30s now, and it's a big event, very impressive, with thousands of kids playing, and it's a party. It's a very special day, in my opinion. So, here, I have a video. Can you help me putting the video? Okay. So these kids are playing, and the boy played there, and now look, the girl is going to do a double dealing move there, and now look, the boy, it's very funny because suddenly he realized he should have think previously, not now. Now he gets the 2 points, but now look, the girl now, it's very funny because she's very happy and he's very sad. And if I had time, I could show the whole video. It's very funny because it's 5 minutes with the girl closing all the boxes after his moves, but I go forward or else Jorge Nuno will kill me. Okay? Believe me, if you want to see the video, I share the video, it's very, very nice. He thinks a lot now. That's another important thing. It's better to think in the key moment, not now. Now he's lost. So now she will be, and this is 5 minutes, so I will skip, okay? Believe me. Okay. So look at this position. This is the key position, and I will give you 10 seconds to look at, and if I have time, I go back later to this position. And now, a little bit of mathematics, that's what I had in my title. So, if we want to play well this game, if we know Euler's formula that relates the number of edges, vertices, and faces in a planar graph, here is the formula without the infinite face. And the key idea, if I wanted to explain this to kids, I will use the idea, talk about this formula for planar graphs and polyhedra in the following way. Imagine you have a ball, a beach ball with a dodecahedron shape, and now imagine that I will remove this face here. I cut this face, and now for this face is open. To be clear, let's forget the picture and concentrate on this drawing. And now we pick the ball and we smash the ball into a table, like this. And now we will open from the face that was cut, we open and we get this planar graph here. And now, if we want to explain this to kids, we might think, what happened to this computation, vertices minus edges plus faces? What happens if I remove a face from outer area, like this? If I remove this face here, if we look with attention, the number of faces decreases by 1, the number of vertices remains equal, and the number of edges increases by 1. It's the same saying that minus edges is plus 1. So this number didn't change. So we have an invariance here. If we remove the faces, if we start pruning these, the number, this calculation, this computation never changed this value. And this is important because it is easier. I'm going forward quickly. It's easier to make this computation if we have a single polygon like this. So we have one face, the number of vertices is equal to the number of faces, and the key idea is that these never change. And it is easier to determine like this, and in the case of a polygon, we have this number is 1. In the case of the polyhedra, this number, if we count with the face that was removed, is 2. And why is this important? Because I have this equation here, and now I'm going to move to dots and boxes. Instead of V, I will use D for dots. Instead of F, I will use B for boxes. And now the number of edges is the number of dots plus the number of boxes minus 1. We have these facts. And now the idea is to go to the gameplay strategy and try to have another formula. So first, the long chain I already more or less defined. It's that situation where a player can get all the boxes or all but one and maintain the control, what I showed in the previous example. So this is a long chain. When this happens and there's a double dealing move, it's a long chain. And we might consider that the number of moves, it's the number of edges, because a move is crossing an edge. But this is incorrect, because when we close boxes, we create new edges without giving the turn to the opponent. So we need to correct this by subtracting the boxes, but this is also incorrect. So we need to take one less, because the last box that is closed, we don't play again. So this -1 is because of that. This is also incorrect. And we need to rearrange the case where we have the double cross moves. So we need to add the double cross moves we made during the play. And this formula is correct, but we still can improve. And because, as I said earlier, the number of double cross moves is usually one less than the number of the number of chains. It's one less than the number of chains, sorry. So, as I showed previously, and now we get these two formulas, and if we rearrange these and we put them together, the first is Euler's formula, the second is by gameplay, we get this. Now, after some cuts and rearrange, we have a very important fundamental identity of the game. Okay, just finishing this, that states the following. The first player wants the number of chains to be a number odds, and the second player even, so players can use this idea to play better. And I finish with this, and if you want to see more examples, please come to me.
Thank you. So now I call Flavia Sancia-Pagosa please.
Okay, there is a small moment for changing the presentation, so I'm taking the opportunity to tell everyone that the dinner today is not close by. We will either have to take a cab, Uber, or go by subway. The dinner is at Real Fábrica, Rato metro station. It's very easy when you get out of the metro station. And anytime between 8 and 8:30, arrival is perfect.
Subway station. R-A-T-O.
The dinner is tonight, yes, and the metro station very close, you just go up, is called Rato, R-A-T-O. If you search for Real Fábrica, Google Maps will take you there.
All right. Hi, everyone. So today I'm going to talk about the game of points and some variations. This is a very well-known game. It's supposed to have started, modern probability theory, as we know. And so I'll describe the game, the original version of the game here, and then talk about a variation of it. So the game of points, also known as the problem of points or the division of stakes problem, addresses how to fairly divide the prize or the pot of a game if we interrupt the game in the middle. So in this case, we're going to have two players playing a game that is made up of several rounds. Each round is worth a point. Each player has the same chance of winning the round. And the game is going to end when one of the players reach a certain number of points. So for example, 5 points. But the game is going to be interrupted in the middle. And then they're going to have to decide what to do with the prize. How should they divide the prize? We can think of the prize as, I don't know, $100. So here's an example. So the first player to win 6 rounds, or 6 points, takes the pot. And so let's say at this point, player A has won 5 rounds and player B has won 3 rounds, and the game is interrupted. So how should they divide the pot? And so this problem showed up in writing for the first time in 1494 in Luca Pacioli's book. And he did propose a solution. Then he said, well, if a player has won 5 and another has won 3, let's just do a ratio of 5-3, right? Player A gets 5/8 of the pot, and player B gets 3/8. And so in other words, he suggested just pay attention to how many points they have now. Don't worry about how many more points they have to go. Of course, these brought up some counterintuitive results right away. So for example, if we think instead of 5-3, let's say only 1 round has been played. And let's say player A has won that round. So Pacioli's solution would be to just give 100% of the pots to player A, which sounds odd, because with 1 round played and at least 5 more rounds to go, the game is still very much up in the air, right? So giving 100% to A doesn't seem like a great solution. So other solutions were attempted following his. They also had their flaws. It wasn't until 1654 with Pascal and Fermat that the first sort of correct solution was proposed. That came from an exchange. They exchanged some letters and went back and forth on approaches, but arrived pretty much at the same conclusion, that the division ratio should be the probability of A winning the game to the probability of B winning the game. In other words, you do have to look at how far each player is to win, so you can compute that probability. So for instance, instead of a 5-3 ratio, their solution was a 7-1 ratio. And this is because when A has already 5 points, the only way that B can win is by scoring 3 points in a row, right? So getting, and the probability of that is 1 out of 8, because we're flipping coins. And so 1 out of 8, 7 out of 8, so a ratio of 7-1. This is considered to be, a cornerstone of probability theory. I won't get much more into the history of this problem, but I do want to point out 2 references that I think are really cool for getting more into that problem. One is The Unfinished Game. It's a book only about the correspondence between Fermat and Pascal. And also the 13 correct solutions to the problem of points and their histories. This is a really nice paper that shows several different ways of solving the problem, including Fermat and Pascal's solution, but also some other approaches like Markov chains, Bayesian statistics, etc. So what I would like to focus this talk on is one of the variations of the game. In fact, there were variations that were proposed. For example, instead of a coin flip, right, maybe player A has a higher chance of winning the rounds than player B, right? So what if it's not a half and half chance? Another variation that has been proposed was, well, what if there's not only 2 players, but there's 3, 4, 5 players? The variation that I would like to look at is one that I haven't seen yet, but I think it could be an interesting one. So it's one in which there's more than 1 point at stake per round. So for example, instead of each round being worth a point, maybe each round is worth 3 points. So A and B are fighting for those 3 points. Maybe A will get 2, B will get 1. Next round, maybe B gets all 3 points and A gets 0. You can think of it as partial credit for each round. We're still going to have both players wanting to reach a certain number of points for the game to finish. And one caveat is that these variation can have ties. So in the original game of points, there were no ties, but now they can end up finishing at the same time because there's more than 1 point at stake per round. And whenever that happens, we're just going to flip a coin to see who gets the pot. All right, so some notation. We're going to use pi I for the probability that player A scores I points in a round. So for example, if there are going to be 3 points at stake per round, we're going to have pi 0 all the way to pi 3. P, x0, x1, et cetera, xk is going to be the probability that a sequence of rounds terminates in player A scoring 0 point, x 0 times, 1 point, x1 times, et cetera. And we're going to have a formula for P, right, which is just the number of ways in which we can arrange those 0, 1, 2, et cetera points. All right, so a little more notation we're going to call PA, the probability that player A reaches y points first. PB is going to be player B reaching y points first. And PT is going to be the probability of a tie. The AB that you see here is the current state of the game. So for example, if A is 5 points to finish the game and B is 7 points to finish the game, A is going to be 5 and B is going to be 7. So if the game is interrupted when A is A to go and B is B to go, then the division ratio should be as in this formula. So the probability of A getting there first plus half of a tie to the probability of B getting there first plus half of a tie. So now in what follows, I will just show like how can we derive closed formulas for that division ratio. So for example, when k equals 1, this is the original problem of points. Right? So if there is 1 point at stake per round, then PA is going to be calculated as, we're going to think of so A winning the game as A scoring the last point, and then is scoring A minus 1 points in the preceding rounds, right? Because here, A has A to go. So that pi 1 denotes that last round, right? So A won the last round. And then here we are adding up all of the instances in which A scored a point in the previous rounds. X0 needs to be less than B, so whenever A scores 0 points, it means that B has scored a point. And we need B to not score more. Actually, we need B to score less than B points. So just, simplifying that a little bit, we get a formula for PA. And because there are no ties, when there's 1 point at stake per round, PB is just 1 minus that. And so this is one of the many ways to solve the problem of points, the original one. But now, here's where things start to get interesting. When we have 2 points per round at stake, then we're going to compute PA by looking at 2 cases. The first case is that A scores at least a point in the last round and A minus 1 point in the preceding round. So we're going to look at the case where A is just 1 to go in the last, not the last, but the one that comes the last. And then case 2 will be A scored 2 points in the last round and it scores A minus 2 in the preceding rounds. So here, we're adding up I going from 1 to 2. So here, because case 1 involves A scoring at least 1 point, right? We're going to need pi 1 and pi 2 as possibilities for that last round. But then we're going to add up the preceding rounds. A needs to score A minus 1 points then, and we need B to score B minus and then 2 minus I, because if A scores, for example, 1 point in the last, it means B is also scoring 1 point. And we want to make sure that doesn't mean that they're going to tie, right? So here we're not computing a tie yet. Simplify things, we end up with this double summation and then 2 summations for the second part. And then to compute PB, we can just use symmetry, right? We can swap x0 with x2, because when A scores 2 points, it means that B scores 0 points and vice versa. We swap A and B, so if we do those swaps in the previous formula, we get the formula for PB, and then the probability of a tie is just going to be 1 minus PA minus PB. So for k equals 3, similar rationale, just more summations, right? So now we have 4 pi's, right? 0, 1, 2, 3. So we just have more possibilities to take into account. So for example, we're going to have 3 cases, right? Because A can win by scoring, by having scored A minus 1 points in the preceding rounds, A minus 2, or A minus 3. And some of those summations will become larger summations, right, when we really try to plug in the correct things. So this is just to give you an idea that the formulas do start to get larger as we involve more points at stake. But there is a nice short way of writing the overall formula for k points at stake. And that would be, right, to like that third summation you're seeing, if there's k points at stake, that's going to become k summations. And we're just going to have to arrange that in a way that satisfies those two. One is an equation and then the inequality below. That's going to become k summations. And again, we compute PB by using symmetry and doing some smart replacements. I do want to make sure I show an example using dice, for instance. So here's how we can play the game with dice and more points at stake. So A and B are going to roll 3 dice each, and each player orders their dice from smallest to largest. They compare the ordered dice, and player A is going to get 1 point for each die that is greater than B, and the ties are going to go to B. We can arrange other scenarios, right? But this is one possible scenario. Under these rules, there are going to be 3 points at stake per round. And the pies are given as follows. We can see some imbalance here, right? This is favoring player B a lot more than player A. And so, in fact, let's say we want to play 10 rounds, 10 points, right? Whoever reaches 10 points first wins. And let's say at the beginning of the game, right, they're both 10 points to go. PA is going to be 0.15, PB 0.79, PT 0.04, so very unbalanced towards B, with a division ratio of 0.178 and 0.822. So it looks like B should pay more to play this game. But here's another example where things are a little more balanced. We can do something similar as the previous scenario, but now A is going to roll 4 dice instead of 3. It's still only comparing 3 dice. So comparing the 3 largest for A and the 3 dice for B ordered. And in that case, so we're still giving ties to B, but in that case, the pies are a little more balanced than before, right? We don't have that clear advantage that B had before. In fact, the division ratio is then 0.524, 0.476, so much closer to half and half. Yes, so this is what I have. Can I answer any questions?
Questions? we are a little bit behind
Yes.
schedule. So I call Gardner Europe now. Carlo will talk about the unfinished game before and after the adventure probability case. Eu faço sinal.
Os 5 minutos ou com o fim?
Sim.
Sim. Obrigada. Yes, so, good afternoon. I will talk in some of the subject that Flavia has just finished, the problem of points. He has at least this other name, unfinished game, or the problem of points. With some differences, of course. I will be starting with this book. It's, well, it should change in yeah, one left, one right. So,
You have two machines, try both.
oh, this one. Okay, sorry, I was looking at the screen only. So, this is a very old book. Sorry, I'm not used to standing still, so I will stand still. This book has been republished about 2 years ago by my professors Jorge Nuno Silva and Pedro Freitas. It's outside if anyone wants to see or buy, of course. And I found very interesting that inside of this book, this was a book meant to teach mathematics over 500 years ago, and it has a large number of recreational situations. One of those situations is the one I'm showing here today. They call it, well, the author calls problem of points, exactly as we said in Portuguese. So in this version, as Flavia already said, there are many versions along the time. So in this version, there were 3 different players. And the game has some arrows, some crossbows, so it's a manly game. He also mentions the prize in stake, 12 coins, 12 doubloons, something like that, and the game is stopped at the scores 4, 3, and 2. So I did some kind of schematic. That's one image from the original, at least one of the old books. It is online. And here we go with the 3 players, their points. The one reaching 5 points or 5 shots, as we want, wins, and the prize is 12 coins, 12 doubloons. So he presents 2 different methods. Surprisingly, at least to me, the first one is a bit longer and opens a window that seems kind of important, at least for those who study this birth of probability. He calls our attention to a value that isn't explicitly on the problem, in the writing of the problem. That's 13 points. Why? That's the maximum value possible in that game. Would refer to the 3 players having 4 points each, and of course the next one will win because we'll get 5 points. So he uses this number, 13, as denominator for the fractions, as we see here on the left. And up in those fractions are the scores that each of the player has at the moment. Of course, when he applies this to 12, he doesn't give away all the money. So there is money left, and the question is how to distribute the value remaining. So what he does next is exactly what we see in other books, actually in his second way of solving this also, That is exactly the fraction each player has in that moment, dividing by the total number of points. So we get fractions with 9 as a denominator. Just as Flavia was saying, this was quite current at this time. So this is the way they thought really should solve a situation like this. And the second method doesn't even, well, this is the final solution when I add the two separate situations from the two steps in this method, and we get, of course, the same ratio, 4, 3, 2. Then we get exactly with the second method that goes directly to the proportion with 9 as a total, as a denominator. For me, while I was reading this, the number 13 at the beginning brought some hope that he might be considering the future, which is, of course, the step that needs to be achieved in order to make theory of probability appear. But unfortunately, he doesn't go along with that reasoning, so 13 is forgotten, and the solution continues the same, exactly the proportions that players have when the game is stopped. So this is my disappointing moment, I think, yep. And of course, when we start looking at math history, Gaspar Nicolas, this Portuguese gentleman, was not the first or the last either, considering this situation. So here, as Flavia said also, in Pacioli's work, I use different colors, but the main thing is in yellow we can see that with 5 and 2, actually they do exactly the number of points each player has, dividing by the total, that in that case would be 11, something like that. And when we get, I don't know, yeah. So here he says exactly if it has 1, 5, and the other 2, I believe this is 50 and 20, and the total being 70, that's the way they are going to get their prize, just in the same proportions. Well, after this, at least staying with greater authors, things start to change. Tartaglia and Cardano are two of the personalities that really assumed there was a mistake in Pacioli's work. And it was quite interesting. None of the authors, Tartaglia or Cardano, had a different proposal, but they were quite vivid, reclaiming that Pacioli was wrong. So Tartaglia says that there's simply no solution, so you just take it to court and let's see what they do. So he follows from there. Cardano says here, we can read the word absurdissimo. I don't speak Latin, but that word I can understand. So he does state that Pacioli was wrong, but he doesn't present a different procedure or an alternative method. And so, of course, we get to Pascal and Fermat. This is one of the tables in their correspondence. I'm not going to each step of this table, but of course we can see there were 3 players, A, B, and C. Those are the letters here, and this would be the first possible play after stopping the game, the second and the third. So we finally see that the future is taken under consideration. So he does worry, or actually they worry, about what is going to happen, what might happen, and in which probability scenario that might, we might see that. So this is one of the possibilities that we could use today to solve the problem with Gaspar Nicolas' numbers, the way he presents to us with 4, 3, 2.
And of course, we get the probabilities completely different to the proposal he does about dividing the 12 coins. Oh, sorry, that isn't obeying me. So now it's all at the same time. It's fine for here. So from the 3 probabilities, we can achieve a proportion that would be 19:6 with the 3 players, which is obviously quite different from Gaspar Nicola's proposal as 4, 3, and 2. So this is the end of my presentation, but I do have 2, 3? Yeah? Okay, thank you. So I'm going to share what happened to me during this PowerPoint. It was a novelty. Some icon that apparently said he was a co-pilot was with me during this time, and at the end he wanted to speak to me and do suggestions, and I let it. So here you have 2 images that he built, and the names are used in the titles, and the time frame, Renaissance, things like that. So this is in artificial intelligence pieces of art, if you think so. I believe these should be playing cards, I don't know. They are strange. And if I was very bad presenting this, here is Microsoft's co-pilot's way of doing my work. So this is what he thinks when he reads my slides. So if I was terrible, probably this might be better than listening to me. So here we go. This is IA working, in this case, for me, and thank you.
Thank you very much, Carla. Now we call Sonia Paes and Andrea Hall from the University of Aveiro. Playful math engages students with non-digital games. You don't have to thank me, but we are ahead of schedule. Look at me, okay?
Ok, vou try. Vou dizer aqui só uma frase. Okay, so just before we start, I'll pick up a sentence that Jim Gardner said in the morning. Surely the best way to wake up a student is to present an intriguing mathematical game, puzzle, magic trick, joke, paradox, etc., etc. And it's within this spirit that we'll make our talk.
Good afternoon. I'm Sonia. My colleague is Andrea. We both are Portuguese math teachers. I teach at Polytechnic of Leiria in the School of Tourism and Maritime Technology. The school is located in Peniche, in this beautiful place near the sea. Andrea teaches at University of Aveiro. Aveiro is a city that also has the sea nearby. Today, we are going to talk, as Andrea said, about playful math, in particular, how to use non-digital games to engage students. Mathematics is one of the school subjects where the motivation, dislike, and failure are frequent concerns. Engaging students in the classroom and utilizing resources that make classes attractive and captivating is fundamental for an effective and fulfilling learning experience. Recreational mathematics through gamification can contribute to engage students in the learning process. Most mathematics non-digital games used in schools are abstract games like X, Go, chess, and checkers. Paula Morando and Maria Luisa Spriafico from the University of Milan have created many non-digital games inspired by classic board games, such as Monopoly or Pictionary, addressing specific mathematics syllabus topics for all levels. We shall present some experiments done with this type of games in several different contexts.
Okay. Sorry, my fault. So we try to adapt and translate some of these games. So these games are in a different spirit. Most of them are also board games, but they really address the subjects or topics that are being taught in the classes instead of just, well, just is a sort of unfair way of speaking about other kinds of games that also develop your reasoning, logical thinking, and critical thinking, and so on. But these games are directed towards the topics that are being taught. And so you can use them in your classroom, use some of your time during the classroom, the classes. And so we did several experiments. The first one was with summer school kids, so that's not a traditional classroom setup. It's a holiday school for kids from 10 to 12 years that universities now throughout Portugal offer to keep the students busy during part of the holidays. We also did a lot of games for undergraduate and postgraduate students, mathematics courses, so both Sonia and I. So that we are talking about university level now, but we also try to teach teachers to use these games. So we did workshops. One particular workshop took place in the Azores and was for pre- and primary school teachers, also for young children. And we also did courses for middle school teachers and high school teachers, and through professional development courses, so longer courses, not just a 2 or 3 hour workshop. And we'll talk just a little bit about some of these experiments and describe some of the games. So the first experiment with the children in the summer school was in 2023, July, so summer, holidays, and at the University of Aveiro we had 20 children and we just played one game for 2 hours, I think, something like that, a nice game that you can adapt to any subject at all. The second, so we did lots of games in several courses, both Sonia and I, so along the last 2 years and even the first semester of the present year also. So we're talking about the Polytechnic of Leiria and the University of Aveiro, as Sonia said, and we're already involved 4 undergraduate courses in tourism and several undergraduate and postgraduate courses in Aveiro for pre-service teachers. And we played several games. We'll only show you a couple of them. For the teachers, we did a workshop in the Azores, as I told you, and this workshop was both for in-service and pre-service teachers, primary schools and pre-primary, so kindergarten children, and we played 3 games during the workshop. Yeah, so that's why I'm looking there and I should be looking here. And we did another workshop for middle school teachers about probability and statistics, and here we played 3 games, and that was an afternoon or morning in September 23. And last year, 1 year ago, more or less, we did 2 professional development courses for teachers. In February, so almost 1 year ago, for primary school teachers, middle school teachers, and high school teachers, and we did a lot of games. It was quite a success, and we'll have a new version which we'll announce to you in the end of the talk. So maybe some of you are interested, and you can still register for these professional development courses, and it's going to be along with the conference. So now we'll describe a couple of the games. The first game is inspired by Monopoly, which is a very popular game. And this is an adaptation that we did. using, so the topic here is a boring topic for most of the students, which is the properties of the operations. Commutativity, associativity, all that stuff is usually very, very boring and complex. At least students show a lot of difficulties. So what's the idea? Is that you can create some kind of title, how do you call it? Sorry. So as you can see, we have properties, in this case, are in the middle of the board, the properties that you want to buy. They're not set along the board. Along the board are the stopping places where you pick up cards that are on the right. So you have several kinds of cards. The money cards, which are the cards on the right that you will pick up along the journey. And in this case, there are properties of the operations, like the property is commutative, or the set is closed for the operation, and so on. So you have closure cards for being closed or being opened, and commutativity and associativity cards, and other properties like having the unit element or having opposite elements, and so on. You need dice and tokens like Monopoly, of course, and you have the title deed cards, which are the things that you're going to buy, in a way, which in this case are couples of sets with an operation. So, for instance, you have the natural numbers with subtraction, or positive rational numbers with addition, and so on. And so you try to collect the money cards, so the properties that can buy the title deeds accordingly. And you go around the board, like in Monopoly, and collect the money cards, okay? So we started with 24 cards in a rectangular form, with a starting one and some lucky positions also, like going to jail or just getting some free money. We also, where are the chance cards? I should have shown them, but sorry, it's going up. Doesn't matter. So we just shuffle the cards and make the board. It can be just randomly. Put the title deeds in the middle. Put the money cards on the right, all the tokens on the start, and then you play like you play Monopoly, going around the board, collecting money, and each time, you collect the money cards as you go along, and when you have enough, you settle a number. We settled 3. When you have 3 money cards to buy one of the properties in the middle, then you can collect it when it's your turn to play, okay? So for instance, if you have the set of even numbers with addition, you can buy it by having this set is closed for the operation. The operation is commutative and has a unit element, and it is in the set, for instance. And then, of course, like Monopoly, you end it either after a predetermined time, or when you get fed up, or whatever. And so here, for instance, are just some pictures of my students playing the game. They did like it, although they don't like the topic, to be honest. And I think it had a good effect. Not all of them learned all about it, but it had a nice effect on the learning.
Another game was Stat Pictionary, inspired by popular game Pictionary. Deals with descriptive statistics such as graphs, frequency tables, and sample measures. And we start by dividing the participants into 2 teams of 4 to 6 players each. The materials needed are a deck of A4-sized cards with statistical graphs or tables and questions, 2 notebooks with the same cards as in the deck but without the questions, 2 calculators, a die, a 3-minute timer. And about the game rules, each team receives a calculator and a notebook. Alternately, a member of each team picks a card and announces its number, so everyone can identify the graph or the table in the notebook. That student starts the timer, rolls the die, and without speaking, tries to get his team to guess the question on the card that corresponds to the number rolled on the die. It is allowed to draw on the board, use symbolic mathematical language, and use colors. It is not allowed to use words or abbreviations, redraw the graph, or any part of it. If the team guesses the question, it must answer it within the remaining time, having at least 1 minute. If the answer is correct, the team earns 2 points and passes the turn to the other team. If the answer to the question is incorrect, the team earns only 1 point for guessing the question, and the other team gets the chance to answer it. They will have 1 minute to do so. If their answer is incorrect, if their answer is correct, this other team earns 1 point. The team with the most points after a predetermined number of game rounds, equal for both teams, wins. And here we can see some pictures of the game in action.
So the question could be like, what's the average number of whatever was represented in the graph, and you have to answer, to guess the question. It's really tough game, but it's very funny, and you really learn a lot with it. So I'll go quickly through this third game because time is going away. So this was a game designed specifically for the Azores. You have the islands. You have teams, 2 to 4 teams. So you have the map, 2 to 4 boats, 1 for each team, an origami boat, whatever model you want. Then you have a 2 dice, a timer, and towers with numbers. So this will be about operations with numbers for small children. The towers, and there are also trophies distributed across all the islands, and the team has to collect all the trophies growing through all the islands. So the first team to collect all the trophies will win. And they start by picking an island, placing a boat on the island. On each island, only 1 boat can be at a time. As I said, the goal is to collect all the trophies. And as you roll the dice, you calculate all the possible results with the normal operations, addition, subtraction, division, and multiplication, and you look for the results on the towers. So all possible results are distributed along the 9 islands so that the probability of all them each island has the same, or more or less the same probability of being picked up, and so you have to travel along all the islands. You can also add more interest, so if you want to address other topics, you can have a deck of cards with questions, and so the teams also have to answer questions about some other topic. So they will travel along the islands and collect the trophies as they manage to get the proper results that are on each island. And you have a timer for that, and so on. And here is a picture of the children playing. They used digital dice because these are dice with 10 results and not so easy to find in common shops, okay?
Another game was Problem Basket. Is a game like treasure hunt style game and addresses problem solving in any context. And we can form any number of teams with 3 or more players per team. As I said, this game is a treasure hunt style game that challenges teams to solve a series of problems. The solutions to these problems lead to the discovery of a magic word. The materials needed are a box containing various objects and mathematical tools, such as ruler, calculator, etc., accessible to all teams. several identical boxes or baskets containing problems written on rolled up pieces of paper. Each paper roll must be attached to an object. The solutions must be numerical and distinct. We must divide the participants into teams, place the box of objects and mathematical tools in a central location, and distribute the problem-filled boxes or baskets among the teams. Each team must solve the problem on the paper rolls. Teams can use the objects and mathematical tools in the central box to solve the problems. As teams solve problems, they should arrange the paper rolls in ascending order based on their answers. On each paper roll, they should write the first letter of the object attached to it. The word formed by the sequence of first letters is the key to the game. The first team to correctly identify the magic word wins the game. These pictures show a problem basket in action and some details of the game. These in particular are from the summer school for 10 to 12 years old that Andrea referred earlier. We can see students using some of the objects and mathematical tools they had in the central box. And in this, we can see them sorting the paper rolls in order to find the magic word. Thank you. And I think Andrea is going to talk
So as I said, we're organizing some professional development courses within a conference. And anyone who is interested, you have here a link. It will be on 21st and 22nd of February, so Friday afternoon and Saturday. And for those participating in the second, so the Saturday, they'll have a second session. The teachers who want to have a certificate 1 month later, because it's they'll have to do some work with their students. It's Oficina de Formação for Portuguese teachers, okay? So thank you.
Thank you very much. I call now Lisa Rochete, who will speak about the problem of things, and Tiago, here. Tiago goes without saying.
Obrigado.
Even though we are ahead of schedule, we don't have more time.
We know. Don't worry.
George Noon, not only are we going to keep on time, but we're going to finish 5 minutes early.
Okay.
So everyone has time to speak in the coffee
Okay, so
break.
let's start.
Let's start, okay.
Good afternoon, everyone. So I'm Lisa. I come from the University of Bretagne Occidentale in Brittany in France. And I'm a historian of mathematics at the Research Center of History of Science and Techniques, the Centre François Viette.
And I'm Tiago Hirt from the Centro Interuniversitário de História da Ciência e Tecnologia. Science, history, maths, magic, those kind of things. And we're going to talk about the mathematical games from the Sphinx.
So it's an ongoing work which started in 2021 in the archives in Brussels. So this talk follows the previous talk we gave at the previous Recreational Mathematics Colloquium in 23. So we will give you some historical contextualization, so you are still updated, and then we will focus on games.
So, as you know, recreational mathematics is a topic that has a very, very long history. Some authors say that it predates mathematics itself. At least it is very old. We, however, will only focus on authors centered around the 20th century. As everyone knows, these tend to create small hubs. So, for instance, Martin Gardner, and thus also the Recreational Mathematics Europe, which is a subtitle to this conference, had grapevine around him, or made a lot of people shine and made these things happen. Similarly, previously in France, we had a circle of people centered around an author, which we will mention further on, Maurice Krajcik. And before, of course, in the English tradition also, you have Ross Ball, Dudney, Sam Lloyd, and again in the French tradition, Lucas Delanois and Lise, short names, will correct my French. We will focus on Maurice Krajcik. Maurice Krajcik was the editor of one of the first scientific journals dedicated entirely to recreational mathematics. After this, we have many more. In the 60s, in the United States, we had the Recreational Mathematics magazine and the Journal of Recreational Mathematics, which stopped publication, unfortunately, in the early 2010s. Currently, we have the Recreational Mathematics magazine, edited by Georges Nounou and some other people. If you are interested, come talk to him. And of course, there are new publications coming out.
Yeah, so as we said, Sphinx can be considered as the first journal entirely dedicated to recreational mathematics. It's stressed in the name, so the monthly journal on recreational questions. And on the cover page, then you have multiple games that we know nowadays that are illustrated, so cryptarism or puzzles such as Chinese rings or bagnodier in French or other games. So it was the first journal, and we can see it as a continuation of another journal that was published previously, the Sphinx Oedipe. So the name is based on this famous format of journal, like asking question and having answer from contributors. So obviously Sphinx raised question and Oedipus just gave answers. And this journal was published and, handily written and published by André Girardin, who is a French mathematician in Nancy. And this journal was published between 1906 and 1926 or 28. We still don't really know when it ends. And it can be really seen in the spirit as the continuation of, the beginning, of Sphinx. Just a word about Sphinx Oedipe. It wasn't entirely dedicated to recreational mathematics. It has other things within, because it was a journal of curiosity and contests, so there was also literacy contests, for example. And then it became more focused on math, especially on number theory and recreational mathematics. So as Thiago said, the Sphinx was created by Maurice Krajcik, so we sketched the biographical elements in previous Recreational Mathematics Colloquium.
Publication pending.
From April 1931 to December 1939.
And Maurice was very well known, and that's how he started the journal also, because of a book he wrote about Mathematique des Jeux, which dealt with, among other things, games, as the English translation would be mathematics of games. It is a recreational mathematics book which has a lot of games in it, which then gave him very much visibility. So today we're going to stress these games, but we'll do so starting from the Sphinx, which had 12 ongoing columns. And these columns ran for the 9 years, for the duration of the journal. And one way that Krajcik and his grapevine had to gather articles for this journal was to create contests. And so he would make these grand concours, and there's at least one per year. And these concours, they always gave out prizes, monetary prizes that, altogether were about 500 Belgian francs, which, I mean, the journal itself cost about 3 francs. Later it got a little bit more expensive. But so these were relevant cash prizes. Other prizes included a box of cigars and, these kind of things. But, and this is the stress we will give, they also included physical board games. And these physical board games, of course, Krajcik also had, what did he have available? The things he invented.
Yeah, so basically this is how a great contest would be presented in a page in Sphinx. So what we highlighted at the bottom of the page is that you could actually buy the game physically at the Sphinx bookshop. So namely, it was a personal COST address because it was also the editorial board's address. And that you could buy it for 4 Belgias, so francs belge, or 25 French francs. So this brings me to the tricolor. So this is the first game that had a contest in the Sphinx. And as you can see, here is depicted the patent COST deposit in 1930 for the game, un jeu de combinaison dénommé le tricolore. So, so we will present the rules of the two games, but separately, of course, and then give you some origins of the game. So it is a really specific board because it's on an hexagonal grid. So not really common. And this is the 2 players version, so you have tokens on each side on the board. And the goal is to prevent any action of your opponent. So you have 3 categories of action. Mainly you can eliminate the pieces, capture the pieces, or blocking the movements of your opponent. So if you have only one single token on a square, well, on an hexagonal square, then you can move only 1 step in 6 directions because there are 6 edges on the square, on the hexagonal square. And if the column has 2 pieces of the same color, then it can move maximum 2 steps, or 3 pieces or more of the same color, then it can move maximum 3 steps. So you understand that you can pile your token on top of each other and create columns. So this is how the tokens move, but you also add like an attack force on your column. So the column has different force, strength, depends on the number of pieces you have in your column, and the color of the square your column is on. So basically, if you are on a red or let's say pink color, and you have 1 token, then the force will be 3. But if you have 3 tokens or more, then the force will be 9. So you have, as you can see, different force depending on the number of tokens and the color you're on. So let's give an example of players who has the blue tokens, and he will play, so the column A, and we will give 2 examples of 2 moves if he plays on the B column or on the C column. So as you can see on the first column, A, the force is 9 because he has 3 tokens. Okay, and it's on the red square, well, hexagonal square. So it's 3 times 3, it's 9. So the force of this column is 9, and the 2 yellow, for the moment, they are captured. They don't mean anything. So blue can do 2 things. Either he plays on column B, and then it will be a capture because the force of the column A is 9, and the force for yellow on column B is 6. Okay, do you follow? It's 2 tokens on a red hexagonal square, so it's 6. 9, yeah, it's better than 6, but it's not twice. Well, it's how can I say that?
So if it exceeds the half of the power of the other piece, it will destroy them, which is case number 2.
Thank you. So in case number 1, the yellow pawns are only captured, so they stay in the column, and perhaps later the yellow player can have it back. While playing in column C, since the force is 2 compared to 9, it's like explosive, and so it's completely eliminates the only yellow token on the column C. So the origins of the game, they are really interesting because, as I already said, it's among the first abstract strategy game played on hexagonal grid. You don't have a lot of games played on hexagonal grid. And it was directly inspired by the chess world champion and German mathematician Emanuel Lasker from the game Laska. So Laska comes from checkers, Chinese checkers, where you can actually make piles, make columns, and you don't kill really the opponent, but you block them and you capture them.
So the other game that we would like to discuss or speak about, the idea in these columns usually would be, can you give us a good mathematical analysis of this? Can you give us good situations, and can you discuss these games, how they are being played? The other game is of a different kind. So instead of having fields which are hexagonal, we have a Mancala board. And this is one of the few Mancala games which is meant to be played by more than 2 players. Usually Mancala games have players pit against each other. Here we have 4 players. It appeared for the first time publicly in the Sphinx in the same year that G4GE put out the Sphinx. And it was advertised and then sold in one of these games. Concours. Now, the idea of the game is to empty all of your pockets, all of your fields, A, B, C, D, E, F, and you are not allowed to use the Roma, which is a field where you can place things, but you cannot take things out. You win if you manage to get rid, I'm not sure if the microphone, if you get rid of all your pieces on your next turn, you don't have anything to play. Then you win. Alternatively, you win if you manage to eliminate all opponents. What does this mean? There is a way to make them do a fault. If an opponent on their last move plays into an empty field, and I'll explain how the moves work in a moment, if the opponent places into this last field, his last piece in an empty field, then he gets a fault. As soon as someone has 12 faults, they're eliminated. Now, this game was inspired by Delanois' Les Jeux de la Chuca, which is a famous typical mathematical puzzle kind of game from the 19th century. Engineer Franklin Punga, Professor Franklin Punga, because he's German, inspired himself in this game. Now, how do the pieces move? They move by sewing. And I'll give you the example with Delanois' game. You have, in this case, you only have 4 fields. You have 1 Roma. And you take all the pieces of one of the fields, in this case, I believe it will be this one, and you sew them, dropping 1 in each consecutive field. That's 1, and that's 2. Then you don't have any more pieces, so you do the next move. There you go. You take, in this case, all 3, and in Chukruma, it goes around, so it will now go all the way here, and it always goes towards the right. In Ruma, the game by Punga, they go around in a circle, so you are giving pieces to the next player. Again, you saw 1, 2, 3 pieces, and again, you take all the pieces, and in this case, you want to make it so that you distribute all of the pieces and all of the fields without ever hitting an empty piece. So if your last move is in an empty field, you lose the game. You don't manage to finish the puzzle, you have to start over. And those are the rules for Chukruma, and this is the way that you move, and which inspired the faults in Roma. Of course, this puzzle is solved since Delanois. He came up with the game. Well, he says it's Malay, but basically he proposed this game and he solved it. And so Edouard Lucas published this, and here you see the first position and then all the moves, so on. So I don't know, just to give an example of something that would be silly, imagine you were to take this 3 and you were just going to distribute, you would end up with empty fields and then you would lose. So this is the solution. Now these games, they have a long history. They are inspired in things that happened before the 20th century, and they get republished. And so for instance, Ruma was picked up and was sold as Deadpan. So instead of having only 4 players, you can actually pick up these plastic pieces and rearrange them so you have 3 players or 2 players. And later on, it was remarketed as Passidon.
For Tricolor, G4GE tried to gather mathematical information about the game. So in every issue, he would say, don't forget the Tricolor game is a really interesting mathematical game, and anyone who has insight or input about this game should write. Well, in 8 years of publication, no one writes in Sphinx about Tricolor. So we assume that we have to do the work now. So Thiago suggested to start to coordinate the positions, since token can move in 6 directions. And that will come, I hope, soon. Future program version in Ludi. So Ludi is a big database with many, like more than 1,000 board games who are programmed, and you can play against an AI, or you can make different AIs playing one against another.
It's also a programming language based on C, I believe, which makes programming games very, very easy, and so you can study these. If you want to know more about this, come and see us. This is all part of the gametable network, which is a COST action.
Yeah. And Tricolor was also commercialized. In 1973, so under the name Tricolor, but also under the name Entscheidung, but the rules are totally the same. And just funny fact, well, not so funny for Maurice Krajcik, but this game, Tricolor, was totally stolen by this Valentin Siena, who is a nickname, but he said he invented the game, though he didn't invent it at all. So thank you for your attention. If you have any questions, just come at the coffee break. And
if you want to come and play the games with us, we have boards.
Or without us.
Or without us. Thank you very much.
So we have coffee break now, and we resume works at 4:10. Okay? 4:10 sharp here. So enjoy yourself.
Hello, everybody. I am Rita Atkins, by profession high school mathematics and physics teacher. I have always been organizing chess conferences. I have also been involved in Erasmus projects, one of which was run by Ludus. That's how I know George from and Tiago from, and a few other colleagues here. I'm also the co-creator of an online program called Logic Board, which is using educational chess for primary school students. Currently, I am not doing mathematics anymore. I'm doing chess and mathematics, a little bit as a secretary of the FIDE Education Commission. FIDE is the International Chess Federation, and our aim is to bring chess into every school in the world in the next few years. It's a very ambitious goal, but chess is extremely popular at the moment, and we would like to do it not as a sport, not to make better and better chess players. That's a good side product, but what we are looking for is chess as an educational tool. When you just have chess as a game in the classroom, you're already doing quite a lot of mathematics. There is logical reasoning, there is metacognition. That's one of the most important aspects, I think, of having chess as a game in the classroom, this teaching the children how to think about their own thinking, especially if you let them talk about it. They let them talk about the game during the game and a post-mortem after the game. They really, really learn a lot from their own mistakes, from their own thinking. Of course, ball coordinates are mathematical. You've got the piece values. Many people think that the only mathematics you can do on the chessboard is connected to chess piece values. I deliberately chose you examples today which don't use the piece values because there are many, many other examples as well. You've got the queening square. The black king has to be within that green square in order to stop the pawn from becoming a queen. You've got the so-called key squares in pawn endgames. That's the top right diagram. If the white king is on one of those squares, then it can always guard the white pawns into the promotion square. You've got the binary nature of the knight. That's also a mathematical concept often used. The corresponding squares on the bottom right diagram where the black king has to match the color where the white king moves to in order to stop the breakthrough of the white king and thus can hold the draw in the game. So chess is already very mathematical. But that's not what I mean by chess and mathematics. For me, chess and mathematics is a collection of games, exercises, and investigations presented by chess pieces or with the chessboard. You don't have to use both of them at the same time. Let me try and explain to you why I think this is important. Let me read you a quick comic strip from Calvin. You're probably familiar with Calvin and Hobbes by Bill Watterson. I'm not going to do my math homework, says Calvin. Look at these unsolved problems. There is a number in mortal combat with another. One of them is going to get subtracted, but why? How? What will be left of him? If I answer these, it would kill the suspense. It would resolve the conflict and turn intriguing possibilities into boring old facts. I never really thought about the literacy qualities of maths, says Hobbes. I prefer to savor the mystery. So it's about savoring the mystery, not turning things into boring old facts, and not killing the suspense. Okay? And how can you do that? You can do that by thinking problems, not solutions. Let children play games. We heard that many, many times today from many of the lecturers. I was so happy with all those maths games that were presented. And you can do that by collaborative problem solving, teamwork, exploration. I think one of the worst mistakes a mathematics teacher can do is, and I'm now talking about primary and secondary school mathematics teaching, not university teaching, is taking away the responsibility of the child from thinking. You probably, if you taught maths in a secondary school, you've probably had this experience when the child puts up this hand. Miss, I don't get this. Sorry, explain it to me. Sorry, I don't get it at all. sorry, this is not good enough, tell me how to do it. And then the teacher tries all sorts of ways with diagrams, with more different approaches. This is the wrong thing to do. Don't take away the responsibility of thinking. It's like one thing I did once, and that was, I think, good success. I had a glass of water, and I took it to this child who was complaining, and I said, I'm so terribly thirsty. Could you please do me a favor and drink this glass of water for me? It's like saying, I refuse to think. Can you please think for me? And I think the child understood what was going on. Okay, so I hope I gave you enough reasons why we should be doing games and investigations in the classroom. And as I am working with chess, I am a chess player myself, and I'm working for the International Chess Federation. One of my jobs is to bring chess in as an educational tool with a mathematics link. You can link chess to literacy, to PE, to art, to many other fields, but my main interest is to link it with mathematics. So some of the mathematics of primary and secondary school syllabus can be actually taught using chess. And why is it a good idea? Because children who already play chess, they really enjoy working in chess themes. They don't think they're doing maths. They might be afraid of maths. You don't need to know much chess to play these games and to do these exercises. Game-based learning, we learned about that a lot today, very important. And the aha moment, Mr. Gardner's aha moment, when you solve a problem on the maths board, very often get this aha moment. And it's really motivating and enhances problem-solving skills in fun ways. A lot of the mathematical problems, but they all belong to the recreational mathematics side of things, are usually quite high-level, university-level problems. But we would like to bring it down to primary school and secondary school levels. And I firmly believe that it is possible. There are some tricks you can use to do that. One is to try the problem on a smaller board. Try an easier problem first. That's, we know it very well from mathematics as one of the main problem-solving methods. Part solving a problem is another one. When you have the 8-queen problem, maybe for an 8-year-old, just make it a 2-queen problem. They only have to find the last 2 queens on the board so that the 8 queens don't attack each other. Working backwards from the solution is also another way to simplify this to a younger audience. And of course, we all like stories. To try and bring your problem and game into a story, bring the chess pieces to life, send them on some great adventures. So the game plan for today for me is to discuss 6 problems on the chessboard for you. Some of them will be games, some of them will be collaborative problems, some can be both, dependent on how you sell it. So let's start with the poison apple. So you've got the chessboard, no chess pieces at sight, and you put an apple, a poisoned apple, on H8, which is the top right corner. You've got 2 players. The players take turn to take ranks and files off the chessboard. You can make it actually a paper cut of a chessboard and then use scissors to make the cuts. You can take both horizontal and vertical cuts, doesn't matter which player you are. So if you are the last one to take the last square, H8, then you win, because then you hand over the poisoned apple to the game partner, and the game partner has to play Snow White and eat the poison apple. So the question is there a winning strategy? And if there is one, then who's got it? So you let the children play. Always first is free exploration. They've got to try, and many of them will actually get the idea. If not, you can always give them hints. The winning strategy is to always cut to a square. So the second player has the winning strategy. And to make it easier, you can try this problem on a smaller board. Now you can make this problem with a twist. This time, instead of a poisoned apple, I'm not saying deliberately healthy apple. So it's poisoned apple. You have some chocolate that you would like to get. So you win if it's your game partner who makes the last cut, because then you get to eat the chocolate. Again, the game is similar but very different in terms of winning strategy. Again, who wins and what is that strategy? This is another problem. I would first start on a small board, 3x3 board, and here you can actually discuss all the different possibilities. Let's say the first player is orange. So you see the orange lines are all cut by the first player. So the first player has 4 possibilities in the first move, 2 horizontal and 2 vertical moves. Then the second player, purple, will cut it into a 2x1 rectangle, and then the first player is forced to make the last move and thus lose the game. So that's on a 3x3 board. Then you can go on an 8x8 board, and then the children will soon realize that at the beginning, the second player has to cut a square as before until you get to this 3x3 square. Then you follow the strategies described here. And if your opponent, orange, cuts the rectangle which is a width of 2 or width of 1, then you just cut into a 2x1 rectangle straight away and win even quicker. So this is a game with a known strategy. Some teachers think it's not good to play games with known strategies after the strategy has been figured out. I am not of that opinion. Kids forget things quickly, 1. Second, they really enjoy winning. So they go home and they play this against their father, their mother, and they'll be very proud, and they will love mathematics even more. So don't underestimate the power of games, even if the strategy is learned and clear. My second one is a problem with trominos. Tromino is there are many different trominos, but I'm just going to consider the 3x1 square-shaped trominos. The question is, which square of the chessboard must be left out for 21 trominos to fit? With a little bit of arithmetic, we know that it's only maximum 21 that can fit, because 21 times 3 is 63, and we have 64 squares on the chessboard. So again, the free exploration starts, kids start drawing, and no matter how many times they try, they come up to the conclusion that one of those 4 squares that must be the one that is always left out. When you do this with little ones, like 7, 8-year-olds, then you can stop here. They're quite happy with the magic, that's the only thing they can do. You can ask them to make as many different possible drawings as they can, and they will do it for you, and they'll be very happy. Of course, you can also bring chess and mathematics into high school, and then you can come deeper into combinatorics and ask, maybe we can prove this. Maybe there is a way to figure out why it must be one of these 4 squares. And there's a rather counterintuitive approach to solving this. It's coloring the chessboard with 3 colors in this or very similar pattern. And once you do this, it's very easy to come to this conclusion. If you've never seen anything like this problem-solving method before, is not so easy, or at least I would never have got it myself. So the key is that no matter how you draw a tromino, a 3x1 tromino on this board, it will always cover 1 of each color, 1 blue, 1 green, and 1 red. Yeah? So altogether, in every possible tiling pattern, you must have 21 red, 21 green, and 21 blue squares that are tiled. Now let's count up all the squares in this pattern. You'll find out that blue is 22, so we have 1 more blue squares than all the other squares. Therefore, the square that we cut out must be a blue square. And just one question remains: can it be any of the blue squares? And the answer is no, because when you turn the board around, the symmetry must be maintained. The blue color has to stay blue after the rotation. So there are only 4 such squares, and that is exactly the 4 squares that we saw at the beginning. This is also a fun problem on smaller boards. And for younger children, I would recommend that you do it on smaller boards, even if it's just for the drawing of the possible tilings, and there will be some squares that are left out, obviously not on a 6x6, but on the others, and can be proved similarly to the 8x8 board. With older children, you can even go 9x9, 10x10, and how crazy mathematicians do, they go all the way to n/n, if you feel like it. One more problem on the board, which still doesn't involve chess pieces. I think this originally wasn't a chess problem, but I'm collecting everything into chess realm because I want to bring them into schools. So now we are going to bring this problem into chess, and we are going to watch grass grow on the chessboard. Stories are important for children. Let's try and bring those pieces and the board alive. So the story is as follows. The chess pieces wanted their bit to combat global warming and decided to grow grass over the chessboard. The most economical way to do this is to lay some turf and let grass spread from this to other areas of the board. Now, turf is very expensive, and it's a square-shaped one with only just 1 unit square of the chessboard is covered. And grass grows from the turf if at least 2 sides of that square is touched by grass that's already grown. So for example, in the diagram there, grass would grow on B7, on G7, H1, D3, and C4, because all of these have at least 2 grass patches next to it. So what's the question? How many do you need to buy at least, and what arrangement should you lay your turf squares in order to green the entire chessboard? Exploration begins even with younger children. Let them draw, give them some starting positions, see if they can green the board. They will come to some conclusions. And one of the conclusions they can definitely find is that they will find these, that some arrangements with 8 turf squares will work. These will green the entire chessboard. And then they will also figure out that some of the arrangements with 8 turf squares will not work. Like in the diagram on the left, only the blue area will be covered, and the diagram on the right as well. So comes the question, can you do it with less than 8? And then if with 8, then can you say something about those 8 in order to make sure that the whole chessboard will be green by the end? Solving this problem requires a little bit of outside of the box thinking, mainly because this is a tiling problem, and tiling problems are usually related to areas, and this is actually a problem which is related to perimeters. And this is like a little shock, but it has a nice shock value, and kids like that. So the question you need to ask is, what happens to the parameter of the total area when the board is being greened? Does the perimeter increase, decreases, or stays the same? So let's investigate that a little bit. And now you can throw it back to them, give them a few diagrams, and then they will come to conclusions. In these 2 examples, the perimeter stays the same. So we were greening here the F7 square. The old perimeter was the 2 red lines, and the new perimeter is the 2 black ones. So we lost 2 and we gained 2. So the total perimeter stayed the same. The same happens on the right diagram. A few more examples. Here, when we're drawing grass from more turfs, more than just 2 on the sides, then the perimeter actually decreases. Like in the first diagram, it decreased by 2. We started with 3 and got 1 extra. And in the last one, when it was completely surrounded on the side by grass, then we ended up with a decrease of 4. And you cannot find any arrangements when the perimeter actually increases, and that is the big key. So the perimeter cannot increase We know that the perimeter of the chessboard is 32. So the lay turf must be at least 32. So 7 squares will not be enough because 7 would have a perimeter of only 28. And it's also interesting to know that these turf squares has to be exactly 32 in perimeter, because the starting and the final perimeter is 32. So at the beginning arrangements, if you go back quickly, here, like the D5 and the E5 squares were joined, so here the perimeter was less, and it didn't work. Here, the perimeter is 32, but it still doesn't work. So this is homework for you to think about why sometimes 8 individual non-connected squares work, and when they work and when they don't work. So this problem is not even as simple as I'm trying to show you now. There are additional depths to be explored. Now let's bring in a chess piece. Let's bring in rooks. Let's look at a game called Sliding Rooks. This is a game we analyzed in depth in the Erasmus project that we did with Ludus. Let me tell you the rules. You've got 8 white rooks on the A file, 8 black rooks on the H file. The rooks can only slide sideways, so the white rooks can only go rightwards, the black rooks can only go leftwards. White starts. And capturing and jumping over the pieces is not allowed. So when the 2 rooks reach the square next to one another, then that's where they have to start. And the last person to move is the winner. Like in many combinatorial games, whoever makes the last move wins. So let the children play this. First, they will play without any meaningful strategy. And then you can give them ideas how to explore the strategy. Don't ever just tell them the strategy. Let them explore it. Start with a simpler game. Just 1 pair of rooks. What happens here? Obviously, white wins. 2 pairs of rooks. Black wins by copying white's move. Like if white makes move from A7 to C7, so moves 2 squares to the right, then one of the rooks, doesn't matter which one, has to make 2 squares to the left, and so on. And then in the second move, white makes 3 moves to the right, and black had to do the same to the left. And then there's only 1 square between them, and then black will win eventually after the next couple of moves. This copycatting, copying each other's moves, is a technique that can be used in many of these games, and another big relevation for children. Then you can increase and make it into 3 pairs of rooks, and they can already see, okay, I can turn this into a 2 pairs of rook game by simply moving one of the rooks to the G file. And then systemize it when you have 2, 4, 6, or 8 pairs of rooks. Black wins with the copycat method, because the game is simply divided into 2 pairs of rook games. And when you have odd numbers of rooks on each side, then it's the first player that wins by turning it into becoming a second player in an even pairs of rooks game. Another game with a known strategy, still kids like playing it. 5 minutes, okay. More interesting, if you want to go deeper into mathematics, problem positions, like the problem on the right, white to move, who has the winning strategy. There is only one single winning move, and it's not easy to find unless you know that this game is closely connected to the so-called NIM games. NIM games are, those games where you have piles of stones, and then you can take as many stones as you want from a single pile when it's your turn, and whoever picks the last stone will win the game. I've got a little movie on that from a mathematics course, so you can take a look if you're interested. I try to simplify it and make it possible for children to understand without delving very deeply into the mathematics of Bouton's rules about nim games. Peaceable queens. This is another mathematics problem. You've got to have the same number of white and black queens placed on the chessboard so that the queens of the opposite color don't attack each other. Start it on smaller boards, 3x3 boards, you can only have one pair of queens, 4x4 boards, 2 pairs, 5x5 boards, 4 pairs of queens, all the way to 8x8, where you can have 9 pairs of queens. I know that lots of mathematicians now work on much larger boards as well. Interestingly, kids, when you give them the chessboard, the 8x8 board, usually get the placement of about 7 queens instead of 9, and then they get stuck. But once I had a 9-year-old who got me this position right, and I'm pretty sure he's never seen this before, so I was very surprised and pleased. So you can do this as a problem solving by putting on one of the armies and then asking the children to figure out the opposite army position. And you can do that systematically by drawing the so-called sphere of action of the white queens. The sphere of action is all the possible squares that the queens can move to. So once you draw that, you see where the possible empty places are for the black queens. The same for the opposite army. And then it is a problem solving you can do with younger kids, older kids, and you can also gamify it. How do you gamify it? You've got to place queens alternately on the board so that they don't attack each other, and then let's see who can place more queens than the other one. And the last one is jumping kings. Let's start with the story. Kings from faraway boards gathered for a conference, and every square of the chessboard was occupied by a single king. A loud bang was heard, and every panic-stricken king jumped an adjacent square. Not a single monarch stayed on his original square, preferring to huddle up to others in his grave moment of danger. In their terror, the kings sought safety in numbers and tried to jump to squares that were chosen by numerous fellow kings as well. They were lucky that the conference was organized on a very large chessboard, and each square was spacious enough to accommodate several kings. Okay, so where do we go from there? Here we have the kings in the conference. Now, after their jump, is this a possible solution? That's the first one that the children usually come up with. And the answer to that is no, because every king has to jump. So even the one in the middle has to jump. So from here, like the one on B1, had to jump somewhere, can't stay where it originally was. Every king was very frightened. So the occupied squares always appear in clusters of 2 or 3. I use the upside-down king as a clusters of kings, so you have many kings in those squares. So investigate all the possible arrangements. There are 20 distinct arrangements. Kids usually very good at finding them. They're all similar to these ones. Practically speaking, I recommend you use double-sided counters, which you put on every square of the chessboard, and every time a king jumps, you turn the counter over to reveal the other color. So you know that the jump has been made, and also that it ended up in another square. And very quickly, I proved it that you have to have at least 12 occupied squares by cutting the board in this arrangement. I'm going to go quite quickly on this, but you will see the essence of it. If we think that only 10 squares can be occupied, then we can always mark with red the forbidden squares where kings can't be, because if they were there, then the clusters wouldn't be able to form, and these numbers wouldn't end up. So these are all the forbidden squares. Then you put the kings there, and now you need to join them into clusters, and to join them into clusters, we ended up again with 12 kings, so you can't do with 10. You can try with the 11 by adding one more in the rectangular sections, and then you put the forbidden squares up again in red, put the kings on the squares where it's possible to have 2, then you choose randomly. Again, you need to make these into clusters. And here are the clusters. But then with the 2 not so smiley faces on D5 and E5, the kings from there don't know where to jump to. So this is not a possible solution. Just one sec. And, and this is when the square, you put 2 kings there. And again, when you put in the clusters, you won't be able to find the correct solution. And this is where I stop. Thank you very much. If you have any more questions.
Building the next generation of recreational mathematicians with Pavilhão students.
You want to check B? See which one it is?
Sure.
That one says only something, right?
This one, probably. Huh? Oh. Welcome. I'm Eliza Gallagher.
I'm Neil Culkin, and we're here to help build the next generation of recreational mathematicians, one digit at a time. Thank you for introducing us to Project 8x8. We're going to talk about Project 9x9.
Exactly. And so we all know the problem, but we think it's good to articulate the problem to start with.
Even though you've already said it many times today.
Many times. All of you are there with us. We know that the general populace, there are a lot of people who are terrified, traumatized by mathematics. And in university, even students who are in science, technology, engineering, and mathematics fields, a lot of them see math as it's just work. It is a tool and it's not fun. It's something we have to do in order to do other things. Even among math majors, we see that.
Yeah. Next. So we have general education classes in the United States because we don't get all of that done by the age of 16 the way you do in Europe. So every student in a US university has to satisfy a course in history, a course in English, a course in mathematics, a course in a foreign language. And some people see this as a good thing.
And we see it as an opportunity. This is our last chance for many of these students before they go on into the general populace. And so students who come in not liking math, who are in that camp where they really only need to take one math class, a lot of them put it off until their last year of university, we would like for them to go out into the world seeing math as fun rather than as something to be avoided.
Yes. I've sat next to people on planes who say, I was never any good at math. Yeah. And somewhere they got stuck. We would like to get them unstuck.
Unfortunately, what we see in the United States all too often is that that general education math course tends to be focused on algorithmic processing, on finding the right answer and putting a box around it. It's often a rehash of math that they've seen before in high school or your pre-collegiate math. So a lot of times it even just reintroduces trauma that they experienced before. So,
and it rarely offers them an opportunity to learn how to think mathematically. They memorize this formula, fill in this box. It's not creative.
And there's certainly exceptions to that, and we know there are people in the room who are doing things in a much better way, and we've enjoyed some of the talks earlier, we're looking forward to some of the talks tomorrow and the next day that aren't fitting this, but very often this is what we see in general education mathematics.
So we see this as an opportunity. And if you see an opportunity, what do? You seize it. So we are proposing a course that is now about to be accepted by our university.
Well, and we are in a fortunate situation. We actually saw this, we tested this out with a smaller group of students, and it has been successful. So we're going to tell you some things about what we've done with a smaller group of students that is now being expanded out to larger populations. So, puzzles. Hello, we all like puzzles, right? We know that this is a good way to go. But convincing folks at our university that this was a good way to go was easy in a small setting, harder in the larger setting. And part of what we went through in deciding what to do is trying to decide which puzzles, because there are so many good puzzles out there. And we could spend a whole semester doing one type of puzzle one day, a different type of puzzle the next day, and so on, and have a wonderful time the whole time through the course. But what we want, especially for the audience of students who are maybe traumatized or terrified of math and don't want to be there, is we want to build comfort. We want to build mathematical depth in a comfortable place. So we wanted an easy entry point, something that felt like, okay, I can do this. They're not asking the world of me.
We also want it to be scalable in difficulty so that we can give them simple puzzles, just the way Rita was talking about giving them 3x3 puzzles,
Yes.
working up to 4x4, 7x7, 8x8. We want there to be a variety of simple puzzles to begin with, but be able to work up to potentially very difficult puzzles.
And by choosing a single type of puzzle, we were worried about being locked into just one sort of type of mathematical reasoning or strategy that students might use, and we didn't want that. We wanted a type of puzzle that would let us use a variety of mathematical reasoning. So we need to start our talk over. Hi, I'm Full Deck.
I'm missing a few cards.
Some of you may know these as our secret identities from a previous gathering for Gardner.
They're no longer secret.
They are no longer secret, they used to be. But these are our identities in the variant Sudoku community, where we are puzzle constructors and puzzle solvers, and have lots of friends around the world.
Exactly.
So, because for us, the answer to this question was variant Sudoku. Almost everybody out there has seen a Sudoku puzzle. A classic Sudoku, where you've got given digits in the grid, and your goal is to fill the rest of the puzzle in with the digits 1 through 9, with one each in each row, each column, and each box.
You've all seen this, right? How many have seen variant Sudoku?
Oh, good,
Good
some
number
hands
here.
are up there. That's unusual. A lot of people haven't. We really like this as a vehicle because it does have that easy entry point. Students come in, they've seen Sudoku. Many of them may even have been bored by classic Sudoku. They feel like, oh, I can do that. Okay? I personally have been bored by classic Sudoku, and it took a while for me to get engaged with variant Sudoku. But with that consistent underlying goal and structure, it creates a scaffold where they feel comfortable engaging in the puzzle, but then we can scale the difficulty. We can construct puzzles or pull puzzles that have been constructed by others to hit the right difficulty level for the students, and also to introduce a lot of different types of mathematical reasoning. These are 5 grids that are coming from puzzles that we've constructed. They have different mathematical constraints. Each of these types of constraint that you see is encoding different mathematical information. And that's one of the things that we do want the students to come away with, is this idea of symbols encode information, and we can encode that and decode that information. It's not the symbols they're familiar with. It is not, let's solve the equation x squared plus 3 equals 9, and to be terrified of, oh gosh, now I have to get square roots in there and what's going on. So it's not the symbols they're familiar with, but the process of encoding and decoding information to represent mathematical relationships is still there. Go.
Oh, what am I saying?
You're talking about this slide.
Oh, this slide.
This is
Sorry. Yeah, I hadn't seen the change in wood. We can't see this on the monitor
No, we
down
can't.
here,
Have to
so
look
I'm
up
happy
here.
to go. Where are we? So we have an online solving platform that we use, and I'm going to talk a little bit about why we like using online platforms as opposed to doing it with pencil and paper puzzles. Pencil and paper puzzles are really good. We have a wonderful platform designed by Sven, who's sitting there in the red shirt in,
right there.
in the back
Wave,
there.
yes.
Wonderful programmer, has built an amazing tool for solving these puzzles online.
And to be clear, he didn't build this for us. We just piggybacked on it.
Exactly.
Yeah.
And one of the things that we have when we use this tool is it keeps information for us. And we're going to talk about that in a little bit. That we can keep track of how people solved a puzzle. Mm-hmm. We can look at the solutions to different puzzles and compare them. Both the solution grid to say, do these puzzles look similar, mm-hmm. and the solution path that students took to get through the puzzles. In addition, there's a huge international community, hundreds of thousands of people solving these puzzles on a daily basis, and there are lots and lots of people constructing these puzzles. There are good construction tools available that allow us to build puzzles with a deliberate solve path. So we can build these to lead students to solutions, to have them find logical solve paths.
Specific types of mathematics that we want to teach, yeah.
And we can make the puzzles pretty. If you like Beatles songs, we've got a Hard Day's Night out there. If you like Beatles songs, we put up Blackbird the other day. I'm turning 64 next March. Guess which one that's going to be?
Birthday puzzles are easy.
Birthday puzzles. We can build information into a grid that make it personal to a student.
So, all of that's nice, but we need to talk about what's the mathematics. Now, we're just going to go through a few slides quickly to give you a sense of some of the variant constraints that are out there and let you think about what the mathematics might be that we could be teaching with these constraints. So, we can restrict cells. We can say this particular cell has to be even and that particular cell has to be odd. We can say that, oh, all of the digits that are orthogonally adjacent to this particular cell need to be smaller than it or larger than it. And there are lots of other cell restrictions that we can put on that will force logic around a particular cell.
Then we can have regions and say this region has to have a complete set of the digits 1 through 9. Normal Sudoku would be the nine 3x3 boxes, but you can build extra regions in. We can have sums where we say these cells in this line and these cells in this line have to add up to the same value. We can have lines where cells equidistant from the center have to add up to the same value. And
so we can wind up with students winding up setting up some simple linear equations or starting to think about parity and the role that that plays. Lots of interesting things that come from line constraints. We could also start introducing modular arithmetic. One of the things that we often get to with the classes is looking at arithmetic modulo 3, which also starts introducing a cyclic feature along a line. So some really fun stuff there. When students discover that they can figure out what the remainder of a particular cell needs to be if you divide the digit in that cell by 3, based on what's going on around it. It's huge light bulbs. They have lots of fun. And these are students, I should say, we tested this class mostly with students in the Honors College, but I've also tested it in the general education class. And the students in that setting were also very engaged and very enthusiastic.
And the students we're going to be targeting are not STEM majors.
Right.
Many of the students we've taught already are not STEM majors, and many of them have said, oh, well, we're scared of puzzles.
Yeah.
But we'll try it.
Right, and then they
And when
wind up
somebody says,
wanting
we're scared of this, but we're going to try it, and then they do, and then they change their setting name to Luna Loves Puzzles. Yeah.
Yeah, it's good stuff. We can also deal with clues outside the grid. So one of my personal favorites is something called an X-sum, where the value that's outside the grid tells you the sum of the first X digits as seen from that clue, where X is the first digit that's seen. And so all of a sudden you wind up having to start thinking about, oh, what combinations are possible? Could I really make 15 in 6 cells if all the digits are different? We start talking about triangular numbers and realizing, yeah, maybe not.
And get us outside and ask us for the one video you want to watch about X-sums and modular lines.
Modular arithmetic. So what do we do in the course? We divide it into 3 units. So the first part is just solving, getting students comfortable with puzzles. And then we move into communicating reasoning, communicating their mathematical reasoning to each other, to us, to the world.
Because it's really important that the students learn how to communicate. It's not just learn how to solve the puzzles, but explain why you made this leap of the imagination. Were you making a lucky guess? Or explain why you said this.
And we're going to talk a little bit more about each of these units in the next couple of slides. I know we both want to say it all on the very first time we see it. But the third unit, and this is the one that actually winds up being the transformative unit for the students, is where they start creating their own puzzles. And this is where, this is what gets us really excited as well, watching them go through the process of realizing that they can make mathematically based puzzles that are intended to have the solver walk through specific mathematical logic.
I remember the first time Eliza gave me a puzzle for Christmas. And I went, wait, you can do that? Ordinary humans can build these things?
Yeah.
And 6 months later, I built my first set of puzzles by myself, not in tandem. And it was like, whoa, this is fun.
And this is from a mathematician, you know, somebody who's been doing this for decades.
Yes.
So in the solving, just as we heard from Rita and from others, we start small, we start easy. Start with 4x4 puzzles, not 9x9. And a big part of that early bit is to develop common language and good notation. So just as with the chess problems, we start talking about rows and columns and locating cells by their name in essentially in coordinate notation. We also talk about ways to keep track of intermediate deductions and a difference between these are the possible values that you could place in a cell versus these are the possible cells where a particular value could go. And all of this is really, again, at that heart of encoding information in notation and using notation as a way to be able to carry out deductions that would otherwise be very difficult, which is, this is why we have algebraic symbols. It's the same idea, it's just a different setting for it. And along the way, we also start thinking about asking good questions. We try to ask them good questions rather than, oh yeah, well that digit would be a 3. We'll say, well, where could 4 go in row 5? And those types of questions.
And then, of course, not us asking them the questions,
Right.
but having them ask the good questions.
Which moves into the communicating their reasoning. Once they're asking their own good questions and answering their own good questions, they're at the position of being able to explain how they made deductions along the way. And we start talking about ideas of proof without necessarily calling it proof, at least to start with, because essentially a careful step through a puzzle is a proof that the solution you've arrived at is unique. And we always emphasize, there's no guessing in Sudoku. This image is one of our students recording a video solve explaining every logical deduction as she solves a puzzle. So, okay. In the creating, yeah.
Yeah, we have our students create puzzles. We have a couple of volumes here with us. We can show you. You can download this for free. Ask us outside where to find this. There are hundreds of puzzles here. They are lovely puzzles. They start from very simple to quite hard.
We didn't think that there would be a need for this when we first started, but they set beautiful puzzles. And they have a good time. This is feedback from the students in reflection. Most of these comments are actually from the students who were not STEM majors, who were taking this as part of the general education course when we piloted it. They're realizing that the importance of thinking logically applies not just to mathematics, but then they can take those logical processes and apply them in history, in the social sciences. They're overcoming anxiety, and they're having fun. We have one student here, oh, it was so much fun. It was more fun than I anticipated, so I made extras.
I did more work than you asked me to.
Exactly. So we feel like that's a success. All right, so we started with the class in just the honors group. The first thing that they did was they said, we're working with elementary school students. Could we take some of these puzzles and use them with the elementary school students? And we said, oh, yes, please. Please, twist our arms. So there's now outreach going on in this project in both formal and informal learning spaces.
We're planning a course for undergraduates, as we've said, and we're also doing research both into math education. Are these puzzles effective at changing the way students approach thinking about them? We're going to be able to look at the solves that they do and analyze them, hopefully using AI to tell whether or not the solutions they get are getting better. Are they proceeding through the problems in better ways? And also, we're going to get them to create puzzles. And one of the things our colleagues said was, how are you going to make sure they don't cheat? So we're developing software to tell whether puzzles are similar. And we have some really good ideas, combinatorial ideas, for how to take two puzzles and say, yes, this one is a copy. No, these are very different. So.
And in a few moments, we're going to put up a QR code if you want to connect with us to find out more about any of these pieces, or if you're interested in offering the course, there'll be a way for you to connect with us. We're going to go through a couple of quick puzzles, quick pictures. These are out testing, and some of our partners in testing these puzzles. We're working with museums and schools and after-school programs. I know. We've been looking at some, these are some of the, this is tantalizing. This is saying, please reach out to us and tell us what these images meant. We have been looking at heat maps of puzzle interactions to start getting at some mathematical reasoning and being able to tell differences in puzzles. We've also been looking at how people proceed through puzzles. This is 1,000 solves of the same puzzle and which cells were placed when and which digits were placed. So that's those ideas of same starting point, same ending point, but it's what happens in the middle that's interesting. That's where we are with this. And many thanks to many people.
Especially Sven.
Especially Sven. And here's how to get in touch with us if you want to talk more. And find us in the hallways. Thank you.
I sent it. Just click, it will be, okay, I went to first, so, okay, sorry there, okay, thank you. Okay, I am going to talk about playing with magic squares, about games and magic figures. We are back to playing and how to make mathematics more interesting through games. I'm moving too much. There are many ways how to construct magic squares. If they are odd, it's very easy. It's what's called the Siamese method. You can do it with kids, and I did it very often in math circles. So on the one hand, you can train the kids to follow an algorithm exactly, and you can also give them back the glass of water if they can check me, did I do it correctly? You say, you check it, because you can calculate the sum of the rows and of the columns and of the diagonals. If the order of the magic square is double even, it's still easy, but if it's single even, which means divisible by 2, but not by 4, things are getting more complicated. There. This is this wants to be a 6 by 6 magic square, but it's not that easy. So there was actually John Conway who thought about a method, and there's this famous engraving of Albrecht Dürer, depicting John Conway thinking about his solution. I just had to take this picture because I'm so happy that after all these native speakers, I'm able to say 2 words correctly and without accent, Albrecht Dürer. So John Conway invented this Lux method, which is based on the odd order magic square. You might remember the algorithm I showed you previously, the Siamese algorithm of moving through the squares, which is basically, which is interesting to mention, to connect it to chess. The moves of how to build the odd order magic square and some moves of chess are connected, and they are historically from the same period. So you move through with the squares, like in the Siamese method, and then if you split every square in 4 mini squares, which turns the 3 by 3 magic square into a 6 by 6 magic square, and you fill the letters like the 1, 2, 3, 4 in the center on the top row. You fill it according to the letters, L, U, and X. If you have a larger magic square, there will also be an X. And this is why the method is called Lux method. This is the third square, which puts the numbers 9, 10, 11, and 12. Still a little complicated, but it works. So we keep this idea of splitting cells of odd order into 4. By the way, I wasn't able to find a publication of Conway mentioning this method, and this we'll meet this more often today, and I feel that my whole contribution to this field is to collect unpublished work. There are publications that mention that Conway invented this method, but didn't find anything of Conway. Then there is magic. Oh, the squares are supposed to be magic sticks. Apparently, I used a phone that isn't here on the computer, never mind. It's not a writing mistake. The game is called Magic. It's made of 6 squares. There's actually 8 pieces in the game because each of the different squares has 3 copies. think of it like if you turn the squares, then the 0 will be on the top corner, then you have an arrangement of 1, 2, and 3 points according to the possible permutations of the numbers 1, 2, and 3 in a clockwise sense. The purpose of the magic game is to arrange 9 of these squares, remember you have 18 because you have 3 copies of each of them, to arrange 9 squares so that the sum of dots in each row, each column, and each diagonal will be fixed. We are back to, will be 9, and we are back to the magic squares. The game was invented by William Baring in 2006. We have the 6 permutations of 1, 2, 3, as I mentioned, and the task is to arrange the magic pieces in a square. So, of course, you can represent the solution numerically with the numbers 0, 1, 2, and 3. And then we get back to the 6 by 6 magic square. And the idea is similar to Conway's idea. We start with a knot or a square. You see on the left, it's the 3 by 3 square, magic square, just that every number appears 4 times. You add a magic solution multiplied by 9, and you get a 6 by 6 magic square. This is also a nice way to teach linear combinations. So what's the problem? We have an algorithm. Any idea what's the problem? The magic solution. It's not at all easy to find. I did it very often with kids, and they got very, very frustrated. Also did it with teacher students, and they got also very, very frustrated. Towards the end of the lesson, I always said, okay, give up the diagonal, just take the row sums and the vertical sums, and somehow they managed, but it's not so nice. We did have an animation, an applet of the magic game in the Davidson Institute. You might remember Yossi's talk this morning about flexagons. It was the same institute. We had an online magic game, just that we did it in Adobe Flash. It's not anymore today. Adobe Flash is gone. Also, this solution, making a linear combination of a split 3 by 3 magic square and a magic solution to get a 6 by 6 magic square, is not published. It like moves through the internet. You can find it. No idea where it comes from. Again. The problem is to find the magic with EDJ solution. Like if you start like this, and you need to fill in the pieces, very often you won't succeed, and you succeeded like with 4 row sums and 4 columns and 1 diagonal, and you put the last piece and everything mixes up. But there's here, like for the center pieces of the border, they are actually easy to fix or easily to find, because you need to satisfy only the row sum and the column sum. The corner pieces are already worse beasts, because they need to satisfy 3 equations. They also need to fit the diagonal. And the center piece is the worst of all, because it needs to fit 2 diagonals and the vertical and the horizontal line. So what can we do? We start, of course, with the most difficult pieces, with the corner pieces and with the center piece. And if you check the magic pieces, you realize there are some that have the diagonal sum 3 and others not, because you put 1, 2, and 3 points and 0. So if you put the corner pieces, if you choose for the corner pieces and for the center, pieces that have the diagonal sum 3, things getting much, much easier, because you can then turn around by quarter terms and the diagonal won't change. It will always be 3. So if you need to fix later the row sum and the column sum, you can turn around the corner pieces, and the diagonal is already fixed and won't change, and this makes it really much, much easier to find a solution. You can also find solutions algebraically. You need a set of I went too fast, sorry. A set of 10 equations. And it's enough to choose the 4 corner pieces, but there will be solutions that are not valid. Like, even if you say that they have additional equations which say that the number of all points in a mini-square needs to be 6, and the product needs to be 0, because there's always a 0 in the number square, you might have solutions with suddenly 4 coming up. So you can solve it algebraically, but you need to exclude some solutions. I move for a moment to another game, but we'll be back soon to Magic Squares. I don't know if you heard of Quattro. It's a game, usually the pieces are usually made of wood. It was invented by the Swiss mathematician Blaise Müller. There are 16 pieces. They are tall and short. You might see it on the picture. They have 4 attributes, and each of these attributes has 2 extremes, like being tall or short, dark or light colored, square or with a circular basis, and solid or hollow on the top. These are the 16 pieces. And the purpose of the game is to arrange the pieces such that there will be one row or diagonal or column with one common attribute. Do you see the solution? Is there a solution on this board? Yeah, it's, well, here. Okay, it was on the next slide. There's a solution because in this column, all of the pieces are light colored. There's a twist in the game, and the twist is that you don't choose the piece that you're going to place. It's a game for 2, and the opponent will give you the piece that you have to place. So you can look at the full glass of water, or of the half full glass of water, that you can decide where to put the piece. Or you look at the half empty glass that you cannot decide which piece to place. In this case, he has no choice which piece he's going to place because she is giving it to him, and she has no control where the piece of the game is going to be. It's an impartial game, which means that the allowable moves depend only on the situation, on the configuration on the board, not on who is going to play. It has the same payoff matrix for both players. Theoretically, there would be something like a number equivalent to the numbers of the NIM game, but it would be way too complicated to calculate it for a Quattro, which is quite complex. So what about strategies? First of all, it's of course inviting to code the pieces. Like you need to decide about the sequence of attributes, which might be height, color, full or empty, and round or square. And then you call the extremes with 0 or 1. And if you do this, and you translate or you transform a magic square to binary code, and you retransform the binary code to the magic pieces, then you see that magic squares can be interpreted as configurations that reflect a tie. So eventually we are back to magic squares. Here you see a tie on the board, you see on the right. And it's not equivalent. There are ties that are no magic squares. Every magic square is a tie, but there are ties that are no magic squares, unfortunately. But this suggests a proposition. I think that perfect mixing can force a draw. If you always try to choose the piece that shares less attributes with the pieces that are already on the board, you can force a draw. And also, if you receive the piece that you decide where to place it on a row or a column where it shares less attributes with the others. The only problem is, like with many games, if both of the players know the trick, it's going to be very boring because both of them will just try to approach the draw, the tie. It seems, and there's again an unpublished publication, I mean, something that exists only as a presentation and as a preprint on the internet. It seems that the game was solved by Lark Goossens in 1908. The many configurations that are possible, he managed to reduce the many possible configurations to a smaller number that he could handle by his PC. And shaking through the possible configurations, he came to the conclusion that perfect players should finish this game in a draw. If you try to analyze the game, there are 3 initial positions, could be corner, border, but not corner, and center. So 3 options to start with. And you just call the first piece 0, 0, 0, 0, and the other pieces you call according to the choices you made for the first piece, but then it's going to get garbled. Because on the second move, you have 8 positions where you could place the second piece, and 15 remaining pieces, because there are 16 altogether. It's not as elegant as, I just want to remember Martin Gardner's tic-tac-toe solution. You have 3 ways to open the game, and then the circles sign mark the places where the second player should answer in order to force a tie. It's nothing like this with Quarto. Quarto is like a higher dimensional generalization of tic-tac-toe, but it's getting very, very complicated. I think that thinking about it statistically can reduce the complexity. We have 8 pieces that share 1 attribute, like the upper row and the lower row. 4 pieces that share 2 attributes, like say there are 4 pieces that are dark brown and high or tall. 2 pieces that share 3 attributes, and 0 pieces that share all the attributes, because each piece is different from the other one. I finish. If you don't have Quarto, use the game of set. And if you don't have the game of set, use your 3D printer. And thanks.
No, slides are not there. Oh, okay, okay. Okay, so we will talk about survey on Richmond bidding combinatorial games. Okay, so okay. So we will first introduce combinatorial games. We have the whole day we are talking about combinatorial games. Then I will give you an example of bidding play, and then we will talk about the survey. Okay. So we have seen these are combinatorial games: chess, Go, 4 in a row, hack and boost. These are some well-known examples of combinatorial games. Tic-tac-toe, nim game. So basically combinatorial games are games with perfect information and no chance move. So whatever is there in front of you. There is nothing hidden. There is no rolling of dice, no deck of cards, no such things. So generally 2 players and alternating play, but this can be generalized. And there are 2 types of winning condition. The one who is making last move wins, or the one who is making last move loses, known as misère play. And so let's see an example of bidding play. Okay. So so this is a game of toppling dominoes. Okay. So there are 5 pieces, 3 are blue and 2 are reds, and players red and blue. Red topples direction means red can topple in this direction or that direction. Only these 2 are the possible directions for red and blue as well. Now let's play this game with bidding. So to play this game with bidding, we have some starting budget. So blue is having 1 rupee, that is Indian rupee symbol. So blue is having 1 rupee, red is having 1 rupee, and this hat symbol is not rupee. It is a tie-breaking marker. I will talk about that, but blue is having 1 rupee, red is having 1 rupee. Okay. So, and we will play with winning condition normal play, where a player cannot move, loses. Okay. They will bid non-negative integer, means 0 or 1, and of course from within their budget they cannot bid 2 or something, and via discrete Richmond auction. We'll talk about that. What is that? So bidding happened, highest bidder won the bid, transfers that amount to other player and make a move in the game. Okay, so we will see several possible bidding cases. One of the cases is this. So blue is having 1 rupee and marker, red is having 1 rupee. Blue is bidding 1 rupee, red is bidding nothing, 0. There. Blue wins by bidding more because blue is bidding more. So blue wins, and sorry about that, but this 1 rupee will get transfer here. So it will be 2 rupees and only marker will be there. So the second scenario is blue is bidding including the marker. So 1 rupee as well as marker, red is bidding 0. So blue wins this bid by bidding more including marker. So the whole thing will get transfer. You see, the whole thing will get transfer here. So this is new budget. Okay. So the third possibility is they are bidding same. So this is a tie situation. So in the tie situation, marker has to shift. So this is a new budget. Okay. So in this case also blue wins the tie because blue is having the tie breaking marker. Okay. So the fourth is red bidding more. Okay. So there are 4. One is blue bidding more, blue bidding including the tie breaking marker. Third is tie. Fourth is red bidding more. Okay. So now we are ready to play. So this is the game position. So this is pre-allocated budget. So now we will play with this budget. So they will bid some non-negative integer. So just suppose both of them are bidding 0. So this is a tie situation. The marker holder wins the bid. So here marker holder is blue. So blue wins the bid and transfer the marker to red and topples the blue domino towards right. So this is the next game position, and this is the new budget. Again the bidding. So here blue is bidding more. So blue will win the bid by bidding more, and so blue wins the bid, transfer that amount to red, and topples the blue domino towards the red domino. This is the new game position. So this is the new budget. Again the bidding will happen, and this time red wins the bid but cannot move, so red loses the game. Okay. So this is a very simple example of how the gameplay will happen. This is not an optimal play, but this is how the gameplay will happen. So game is there, bidding will happen, winners will get decided, and the winner will make a move. And if you notice, this amount is getting transferred from here to here and here to here. So this is Richmond auction. Okay. And the bidding is discrete. So they are bidding 0, 1, that type. They are not bidding half rupee, 0.4, something like that. So that is discrete. So this is discrete Richmond auction. Okay. So once we have seen this thing, then we'll talk about from where this has came. So the origin of this thing. So it started with these, not visible. So these are the first 2 papers which appeared after the death of Richmond. They have talked about this very nice property about random turn game, and then how bidding is giving a perfect result. So to get into that, we will see this random turn game. So there is a token here. So there are two players, and a fair coin toss decides the next mover. If you are left, your aim is to reach here. If you are right, then your aim is to reach here, and this is a directed graph. Okay? So in this example, it's very easy to see that if we will toss a fair coin, then left wins with probability 3/4 because this, and right wins with probability 1/4. Okay. So now let's see Richmond version of this. Is also called as double reachability game, because one of the player aims to reach one target, another player aim to reach another target. So double reachability game. So now again this is a directed graph. They have left has some budget x, right has some budget 1 minus x. So now this is real number. Okay, and they can bid non-negative real number from their budget. Okay, and the same thing, highest bidder wins the bid, transfers the winning amount to the other player, makes a move in the game. Okay, the winner will make a move in the game. And one thing to notice, these are real numbers, so they will bid non-negative real number. Okay, so just an example here, we have token. This left wants to come here, right wants to go there, and just for example, consider left's budget is this, and left bid 0.1, right bid 2, 0.2, then right wins the bid, transfers the winning amount to left, makes a move in the game. So this is new game position and new budget, because 0.4, so right transfers this amount to here, so 0.4 plus 0.2, 0.6. And this is right's budget. And now again left will bid, left is bidding higher, and left just wins the bid. So this is new budget. So this is the Richmond version of double reachability game, which they had introduced in their paper. And so now resemblance between this, the random turn game and the Richmond version. Random turn means just coin toss will decide the next person, and the Richmond version. Okay, so if we have seen that if in a Richmond game, if this is the current budget, then left is winning the game. So now the question is, what is the minimum budget, left budget, to ensure her win? So it's easy to figure it out here, that if left is having 0.25 plus epsilon, then left can ensure her win. Okay. So this is, if we recall that in random turn game, we have seen that the probability of left's win is 0.75 and right's win is 0.25. So there is a relation between this, the left budget, what is the minimum left budget left required to make sure to win the game, and this probability of left winning and right winning via just a random coin toss, fair coin toss. Okay. So they had actually proved that there is a threshold budget above which left secures victory. Okay. So they exist given a directed graph, given the token where it is placed, there is a Richmond cost above which if left is having more share of money than that, then left wins. Left can of course optimally, and if left is having less money than that, then right can secure win. Okay. So this is the relation they had found. And another important result is for acyclic graph, they found a constructive approach. It's not just you find out randomly, but they found a constructive approach in which for each nodes you can find a Richmond cost, and you can go via backward induction to find the top node, the root. Okay. So, and they have also extended this result for an infinite graph, and they are basically able to prove that if you have if left share of money exceeds this part, then left wins. If below, then right can make sure he is winning, and if the share is in between, then the game will end in a draw, means if they will play optimally. And the thing is, Richmond cost is not necessarily a rational number. So they have also given an example where this Richmond cost is coming out to be an irrational number. So, so this is the infinite duration game, and so double reachability game, infinite duration, double reachability game. So here left wants to go here, right wants to go there. So this Guy Avni has done research and say infinite duration game, but different graph. Now they have studied on parity game and mean payoff game. These are two type of game, and for those games they have showed that with Richmond bidding a threshold budget exists for both parity and mean payoff game. And so one of the major limitations with bidding with real number is, in real life you cannot play. You cannot say I will bid pi, I will bid e. So making calculation with that is not an easy thing. So this is one of the major limitations. And they studied symmetric games, means both player can make a move to that direction, may not want to make a move, but can make a move. Okay. So then this Sam Payne and Mike Devlin studied, discretize the bidding and also make it partisan. Okay. So here blue edge, red edge showing blues move, reds move, and again the target node, means if game is ending here, then left will win. If game is ending here, then right will win. And if game is reaching there, then it is a tie. Okay, I will just go to the result. but here there is one modification in the bidding. So highest bidder wins the bid, transfers the winning amount to the other player, but so the winner of the bid decides who moves next. So this is different from the earlier rich man. In earlier rich man, the winner of the bid will make a move in the game, but in this champagne discretized version, they have made it decides who moves next, and they made it like this to model the zugzwang position. Zugzwang positions are those positions where nobody wants to make a move. And the thing is, tiebreaker comes into play only in tie. This is contrary to the example which I had shown. In the example I had shown, there a player can intentionally give away the tie-breaking marker. So you recall, so there were 4 possibilities. Left was bidding more and winning. Left was bidding more, including the tie-breaking marker. Then there was a tie situation, and then red was bidding more. So this thing is important. Okay. And this with their rule, they have shown that if you have 5 rupees and you have option to have the tie-breaking marker or an additional 1 rupee, then both of the option is advantageous to you, but having this extra coin is more advantageous. This is what they have proved. And they have proved the existence of threshold amount like earlier, and they have studied the game of tic-tac-toe extensively in their bidding setup. And this Larson and Wasland has studied this end games in bidding chess, and the same setup, but they have modified the bidding rule, and they tried to model zugzwang position in a different way. They introduced negative bids. So now players can bid negative, means I want other person to make a move. So they have their different bidding scheme, and for that bidding scheme, they have shown again the existence of non-trivial interval, and this. So there are this alpha, beta, and so in random turn play, so maximum probability that left can force a win, and in bidding play, a minimum amount right needs to avoid losing, and maximum probability that left can avoid a loss. So minimum amount right needs to force a win. So this they have proved for this partisan game, but so this is another example with such a non-trivial interval, which we had seen in infinite duration gameplay. We had seen a non-trivial interval where if the left's money is more than RV, then left is winning, and below 1 minus RV, then right is winning, and in between there was tie. So so the limitation of these things is these things cannot be extended because they are trying to avoid zugzwang positions. So the example of gameplay which I had shown earlier is our proposed bidding framework, in which we are not trying to avoid zugzwang position, and with that bidding rule, we can actually study the whole combinatorial games, and alternating play in fact becomes the special case. So with this like references, and thank you.
Okay, so I'm gonna try to go fast because I have only 10 minutes. I have never done anything in 10 minutes. So let's see what happens. Anything? Okay, let's see. Okay, so here we are. My name is Andrea Gani. I come from Madrid. I'm part of a project called Divermates, which is like fun math. It's not diagram-mate, however. We have developed something really fun, which is called ectoedra. An ectoedron would be a polyhedron with 100 faces. So let me tell you a little bit of history. We do summer camps, we do workshops, we do lectures, and we do a summer camp and for kids. And we are very fond of talking about mathematicians of the history, because I don't know why, but people don't know many mathematicians. They know painters, they know singers, they know stuff, but they don't know mathematicians. So we developed collection cards for the kids. So every day we gave them cards, 10 of them. Like, okay, I give you 10 KD Lamar's, I give you 10 Gauss, I give you 10 Pythagoras or 10 Hipparchus, and they went to the recess. Really, they needed to make a whole poster, which is this one here. So they were very excited to get the 40 of them. So they were going to the recess like, hey, I give you a Gauss, you give me a Descartes, you give me a whatever. So at the end of the week, 50 kids, they knew already 40 mathematicians. That is really exciting. This is really exciting. The first thing we did was this poster. They have to fill it up, all with mathematicians. Then we started to create object with these collection cards. So they made these hypercubes. Then we did this rhombicosidodecahedron as well, so they could have this at home. They could use it as a lamp as well. And there was another thing we do in our summer camps, which is playing games. We in the first edition we went with big boxes of games, like many games. And it was a problem because there was a time when we split camps, so we have to decide or spend much more money. So with time we decided that we put those things together, and then we create Divermates, which was a deck of cards with 72 mathematicians, and we could play with this. So instead of having a big box of many games, we have only a small suitcase with 20 of these, because with these cards you can play many things, okay? This was like the beta version of something we didn't know it was coming. At the beginning it was just fun, and they liked it, but it's not friendly, let's say, okay? And it has something else. We, by chance, talking with a guy who worked in an app creation company, we made a 3D augmented reality thing. Okay, it was really cool, it worked really well, and then ectoedra happened. So, what happened with ectoedra? of 72, you have 100. Still, we have people left out of the together, many of them. We have them drawn by an artist, so they are really more kid-friendly to see. We have more games, and we are growing every day. We adapt games to play with the together, and we have many games that you can play actually with the box. You have already like 2 of them, okay, that you can play here. Really fun. Very important for us is that we only put games that we could play at home. I mean, for us, every now and then, they play games in the school that they are not so fun. I mean, if I wouldn't play this game with my friends, it's not a game for a together, okay? So it has been fun. We improved the materiality, and we actually added 2 games in the app as well. So you can now we have like 4 games, and then you have to go at this. It's gonna be even easier. So let me see if this happens. Hello. Okay. Magic. Okay, so this is some of the faces you have here. Videos, rabbits. Oh, each card has 4 things. You have the color. Okay, you have 8 different colors. You have this number here, which goes from 1 to 10, and then we start with every 10. And this one we call the ectoindice, that goes from 0 to 100. So if you go from the beginning of the times, you have all the Greeks, okay? Then you have here, we try to be as inclusive as we could. So we put as many women as we could, and we put as many nationalities as well. Okay, so you can find Yugu, of course. That we have many of the Spanish ones as well, okay? And all the Italians, Newton, they are the good ones. And of course, we have one of our fathers, which is Martin Gardner here, okay? So we have many of them. Let me show you how the app works. First, you have to know that it has very sexy music. Okay. Now I'm going to turn it up, otherwise. So, when you get, it's all, once you download the app, you're it alone. So, if you get like that, you have here the face. Okay. Here you have the biography with him, with a link to more about Thales, and then you have three something of why he was famous. Okay. In this case, do something with a pyramid and the sun. You can get like movies, for example, so you get like it. Go. Okay. So you have here, see. And then again, let me show you one of my favorites, which is this one. One of the hidden figures. you put it there. So you have fun and you learn. Did you have fun? Yes. Yes. Did you learn math? Yes. Did you learn math? There you go. I have a box with 36 of them. I'm going to be there outside there. Any one of you, normally it's 35 euros. We're going to have them for 30 euros. So, thank you.
For market shop.
Yes.
Is it in English?
Oh, yes, very good question. We do not set questions now. But no, it's, we are preparing a Kickstarter, so it comes in English. But the app is not in English.
Okay, thank you. So,
Let me take this off here.
Together. One system. Yeah. So, because we were in separate.
Dá-me o telemóvel.
Qual é que é o pointer?
Acho que é este. For keynotes only. Okay. Qual é que é o... Não, mas falamos deste aqui, não?
Ok.
Ok. Podemos começar. Acho que é este. Ora? Okay, so let's get started. Ladies and gentle people, welcome. Everyone has heard about the hangman game, but we've decided to extend it. And most people would ask us, well, why? But we're mathematicians, so we answer with why not? But the real reason why we decided to do this game is because, well, we were bored. On a good Sunday afternoon, we wanted to grab a coffee, and suddenly I asked Francisco, well, guess my number. And from there on, everything started.
So, the usual game of hangman is you start with a configuration like that, and you try and guess a word, and if you don't guess the word, then game over and you get hanged. So, Leon, guess my word.
How about an A?
An A. Yeah, it's there.
It's there? Perfect. How about P?
P? Not really.
Okay, I lost my first life, no problem. How about an E?
E? Not really. Not again.
Okay, but now I know it. How about an M?
M? Yeah, it's there. Perfect.
Okay. Last chance, what about a T?
A T is also there.
I think I got the word. Is it by any chance math?
Yes, it is.
Amazing! Hooray! Thank you very much. But let's actually talk about the real reason why we decided to do this game.
So, the usual hangman is we guess a word by trying to guess letters. In our math hangman, we try to guess a number by asking the right questions about the structure of a number. Well, the first one, kind of boring. The next one, well, we use number theory to discover numbers. Everybody wants that.
So we are assuming that we have 7 lives, and this is the way the configuration moves on. So we start with 7 lives, and the game is over when we have 0 lives. So the mathematical version of the hangman game starts with 2 players. Player 1 asks a question about the structure of the number of the number that we're trying to guess. And then player 2 gives an answer, either a yes, a no, or a number. And then player 1 has to give a guess, always. And then we have 2 possibilities. Either the game ends because the guess was right, or the guess is wrong, and, well, we lose a life. So let's actually give an example. Ladies and gentlemen, gentle people, from the Portuguese committee, we have Tiago Hirt, and the international challenger, we have Colin Wright. Fight! But let's not always put their pictures, so let's simplify the representation. We will have Colin represent like this, and Tiago like this. I guess
let the battle begin. So Colin is asking Tiago, guess my number. Tiago thinks, and maybe he just tries to say, well, is it 805? Well, this is not a good question, come on, because seriously, the probability of winning is just, well, 0.11. We don't want this, let's make it better. So maybe Tiago can do a better question and say, well, is your number a prime number? We all love prime numbers. But then Colin says, no. Okay, what was the rule? Now Tiago has to give a guess. So Tiago says, well, okay, if we know that there are 143 numbers with 3 digits and only 15.89% of them are prime, how about, well, is it 302? And Colin answers with, no, of course not. So what happened? Tiago just lost his first life. Let's move on. This is not enough. So maybe let's talk about, how about, what's the lowest natural number above the square root of the number? I know it looks complicated, but look, it's just, well, the answer of Colin is 22. And this means that the ceiling function of the square root of n is 22. But no worries, what does this mean? Well, it just means that the number is, well, the square root of the number is 21 point something. But this allows us to conclude that, well, the square root of n has to be between 21 and 22, and hence the number itself, n, has to be between 441 and 484. Okay, but this is not as amazing as it could be because we still have 44 possible numbers that we can guess. So let's move on, and we say that Tiago says, okay, but is it 449? And Colin answers with, no. Exactly. And this means that Tiago has lost another life. We went from 6 to 5. So until now, what does Tiago know? Well, he knows that the number is not prime, and he knows it has to be between 441 and 484. So what could we do? Well, between these two numbers, there are 37 composite primes. This means 37 numbers that are not prime. But the probability is still not as good as we would like to. So let's continue. Let's talk about prime factors. Now Tiago asks, how many distinct prime factors does the number have? And Colin answers with 3. And mathematically, we could say that, okay, our number n looks like this. Don't worry, it just means that we have primes p1, p2, and p3, and they might have, like we might have 2 times 2, times 3, times 5, doesn't matter. And Tiago asks, okay, but is it then 442? And Colin answers with, no. Correct. So he says no, and we have a problem. Even though Tiago's guess was okay, it was still, so we had 2 times 13 times 17, it's still not good enough. And Tiago loses another life.
So the situation is dire, really. So we know that the number is not prime. We know that it's between 441 and 484, and it has 3 distinct prime factors. Well, a good idea for us, it would be if we can actually find those prime factors. And we could ask questions like, is it divisible by 3, is it divisible by 5? And this eats up a lot of questions. So instead of asking directly, is it divisible by a number, we're going to ask what is the greatest common divisor between our number and a very specific number. In case you do not remember, 30 is 2 times 3 times 5. So with this question, we can test for divisibility for 2, 3, and 5 at the same time. Amazing. And so Tiago asks this question, Colin answers with 2. Now we know that the greatest common divisor between n and 30 is 2, so 2 is one of those distinct prime factors that we knew. And then Tiago wagers a guess, is it 646? Well, this guess is okay because it's an even number, but hang on. 646. Well, Colin answers no, obviously, because, well, show the next one. It's outside of our bounds. It could never be something in the 600s. So instead of losing just 1 life, we lose 2. Oh God, that's not good. So how about we try the same strategy with a different number? So now let's ask what's the greatest what's the greatest common divisor between n and our number, which will be 1001. In case you don't remember, it's 7 times 11 times 13, which would be the next 3 prime numbers. Colin answers with 7. In other words, we know now that 7 is a divisor of our secret number. We now have this way to write it, and Tiago wagers a guess of 476, because 476 can be written like this. And now let's check if we actually don't incur in a contradiction. So 1, it's not prime, good. It's between our bounds, perfect. It respects the greatest common divisor. It respects the other greatest common divisor. So, and we have 3 different prime factors, perfect. Now, will Tiago survive? What do you think?
Oof.
Oof.
Little
Oof.
faith, little faith.
Now, Colin is thinking, so let Colin think. Good. And Colin answers with, yes! Hooray! And Colin just lost. Wah, wah.
Okay, but this was an example, but a big fight, actually, between 2 great people. But let's consider something else. Life is actually hard, right? So we did an example with 3 digits. What we have considered 1 digit, we had 9 possible numbers. With 2, we have 90 possible answers. Well, with 3, like we saw, 900. With 4, 9,000. And this can be actually modeled with a function which is plotted like this. Look, it's exponential. Horrible. This means if we choose to have more digits, it's going to become increasingly harder, and we have to start thinking, okay, well, what are the best questions and what are the worst? What's the best strategy? Does it change between the amount of digits? And finally, which questions should be allowed and which shouldn't? So, guys, everyone knows the saying, a mathematician is a machine for turning coffee into theorems, right? Well,
as we like to say, actually a bored mathematician is a machine for turning coffee into games.
Thank you very much.
Thank you. Okay, and now it's my turn. And now I've come to talk about the wondrous world of twisty cylinders. So let's get started. So let's go a few years into the past, and it's 1974. Whoops, the other way around. 1974 rolled in, and God said, let there be Rubik. And so we have here Erno Rubik with the original prototype for the Rubik's Cube. This is not the version we know, because in 1980 we actually got the version we all know. It got featured in toy fairs, and it's kick-started the twisty puzzle revolution. And that's the life we live on right now. So I'm not going to talk about the Rubik's Cube. That's been done a lot. I'm going to be talking about a different puzzle, which is known as Rubik's Cheese, which is the one on the right. It was made by Erno Rubik in 1980. However, I'm not going to talk specifically about that one. I'm going to talk about the one on the left, which was projected by Anthony Greenhill in 2002. So, inner workings of the cube. First of all, the cube cylinder. Each row is independent, and it flips along the 6 dividing lines, which are the 6 vertical lines that I have marked over there. Now, when I was studying this puzzle, I represented it as a rectangle numbered like this. And in case you'd like to see some colors, here you go, have some colors. Now, the cool thing about this puzzle is, 1, it rotates. Hooray! And the good thing about this rotation is that it is reversible. Good. So we are in the presence of a group in terms of rotations, which is great. And the first row rotates, the second one as well. Fantastic. So we have already some good structure going on here. The other thing that this puzzle does is, well, it flips. What do I mean by flip? Well, this. Hang on. There you go. It flipped. And this is also reversible. Look at that. Amazing. And we can choose a different flip line. So we can choose that one, and that also flips like this and like that. So now you know how the puzzle really works. Look, I have ones right here, but I really wanted just to project this. So an interesting thing about this puzzle is that the solution is not unique. I would like now the technician to focus on me, please. Can I get... Okay. All right, you can see. So, as you can see, this is solved, and I have numbered it. Whoop, there you go, thank you. So, and I have numbered it for convenience, right? Now, let me show you how this solution is not unique. So, if we do this combination of moves, and two, and another one, look at that. It is solved again, but now the columns have permutated. So this looks easier than the Rubik's Cube. The solution is not unique, so that's great. So how do we start solving this? Can we return to the slides, please? Great. So we start with an unsolved cylinder. I have one right over here. And we can always have set the first column. So I have one right here, I can rotate it, and bam, look at that, first column, and look, again, I also have an animation, so in case you didn't see it, here you go, there's that. Unless the cylinder looks very similar to this, in which case you cannot easily rotate it, you have to do a flip, and then you can do the rotation all over again. Perfect. Now, before I studied this cylinder, I studied a very similar twisty puzzle, which is this. Can I ask the technician now to focus on this one over here? So this over here, can you guys see it? Yeah, it rotates like this as well. And it has this empty void over here that can just change places, rotates, and then gets placed over there. All good? Yeah? So, inspired on my studies of this, what I did is, can we get back to the notes? So I started studying the commutator of these operations. So let's see how this will look like with the rectangle. So we go. So imagine we do, oh, is it the other one? Oh, there you go. Okay, good. Okay, let's go back. So let's say, so we start like this, then we first rotate, we flip, we reverse rotate, and we flip again. So let's compare what we had at the start and what we have at the end. Can you see anything that stayed the same and anything that has moved? In case you're not seeing it, well, this is what we have. This commutator, what did is that it maintained that sector in blue untouched, and it flipped and it cycled through those 7 pieces. Well, this is what we will do to sort half of the cylinder. So let's go back to what we had before. We had a already set column, right? We had this. And imagine I'm going to set the orange piece over there. We can always put the cylinder in a way so that we can cycle through the pieces and set the second column. Great. Now what we do, we rotate the cylinder again, and now we want to sort out the gray piece, and then we do it. Great. So with just a simple commutator, we managed to sort half of the cylinder. Great. Now here's the deal. To sort the other half of the cylinder following this technique, it's a case-by-case process, and it would take me some time to actually go through it. So I'm going to leave the second half for some other time. If you'd like to see how I do it, I have here my yellow book followed with lots of diagrams and all of my studies. It's like 47 mini pages of permutations. I'm going to start talking about the other thing. So now, let's pretend that we have everything sorted. All of the columns are sorted. And when columns are sorted, we might still get this over here. We can still get these faces. All right, perfect. We can still get these faces, not with the same color. And that's what we want. So how do we prove that we can actually get to that configuration? Well, that's what I then studied. So here's the deal. Imagine I have two colors, green and blue, and I want to have an entire face just with blues, an entire face just with greens. So it's the same thing of actually setting up, well, trying to find out what permutations would have this all zeros, 0, 0, 0, 0, 0, 0. And also, by the way, I've made a scheme of the cylinder to look like this. This is what we want in the end. Now, I don't know about you. I know if you're doing some quick math, but if I have six places and I have two colors, well, 2 to the 6, that's 64. I have 64 possible strings of zeros and ones to inspect to see if I can always get to the original one, the one with only zeros at the top and ones at the end. And when I reached this, I thought, oh my God, this is absolutely terrible. I'm not going to check 64 strings. Well, luckily for me, I had an idea. It felt like Christmas. First, because it was an amazing idea, and second, because it was the 25th of December. It was actually Christmas when I got this. The thing is, if I hold the cylinder like this, or like this, or like this, or like this, whoops, there you go, or like this, or like this, or like this, nothing will change. I will still have a cylinder. I will still have a circle. And what I can do is I can use the rotations of the hexagon to actually sort that out. And I can use, well, I was so amazed by this because I got to use my favorite theorem in math. What were the odds? I got to use Pauli's enumeration theorem, which counts the number of unique configurations that one could have with respect to symmetries. Great. So what happened was that instead of the 64s, by the way, let me just show you my calculations. So these were the actual calculations I did on Christmas. Everybody had fallen asleep and I was doing math, which is great. And with this, I just substituted x for 2, as Pauli's theorem tells us, and I got 14. 14 is much easier to actually check than 64. So what did I do? I drew all 14 configurations, and I've labeled them A, B, C, D, and so on. And then what did I do? I tried out movements. All the movements I had studied up to that moment, I studied them, and I got this very confusing diagram. Well, for me it makes sense, but look at the arrows all pointing to A. A was our original configuration. So following those movements, I could always get from any configuration of greens and blues that I have over here to my original one. Great. And so here's the deal. I've just shown you, 1, how to sort half of the cylinder, and how to sort the top and bottom faces of the cylinder. Now, this is the part where I have some further questions. First things first, how many different configurations are there really? Because, well, I've analyzed it through Pauli's enumeration theorem, but I don't really have an answer for how many configurations I have. I have just, look, if you consider a rectangle, like this one, and you consider that we have 12 spaces and 2 colors can permute, I mean, this is my upper bound. I'm not going to get much more than this. But this is not an answer. This is just an upper bound. Maybe I can get this much, 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 much lower, and that's what I expect. The second thing is really, how can we fully describe the symmetry group of this puzzle? I'm still working on that, but so far, no clue. And lastly, this is a 2-column puzzle. I would like to have a 3-column puzzle, like this, to see what I would have to change. I've searched online. I couldn't find it. It apparently went out of stock. So if anybody locates one of these puzzles, I'd be more than grateful. And so in the end, for all of these questions, I got nothing. Thank you. Hooray!